Imagine a creature that looks like a giant woodlouse, a pill bug the size of a football, an animal that is, in every structural way, identical to the small gray insects you might find under a garden rock, except that it is 50 times larger. It has the same segmented armor, the same slow waddling legs, the same ability to curl into a defensive ball. But this creature does not live under a rock in your garden. It lives under an ocean. It lives in a world of total darkness, at depths of over 2,000 feet, where the temperature hovers just above freezing and the weight of the water above it is measured in tons per square inch. Its name is Bathynomus giganteus. It is the giant isopod, and it is the first and most accessible example of a strange rule that seems to govern the deep ocean. The rule is this: when you go deep enough, when you descend past the reach of sunlight and into the permanent midnight of the abyss, ordinary things become extraordinary. Small things become large. The rules of size that apply to the surface world begin to bend and stretch and break. This phenomenon has a scientific name. It is called deep sea gigantism. And if you have never heard of it before, you are not alone. It is one of the most fascinating and least understood biological patterns on Earth. The basic observation is simple. For many groups of marine animals, the deeper you go, the larger the individuals become. A shrimp-like amphipod that measures half an inch in shallow waters can grow to over 10 inches in the deep sea. A tiny ostracod, a crustacean no bigger than a grain of rice at the surface, becomes a creature the size of a large olive when it lives at 3,000 meters. A jellyfish that is barely visible in the sunlit zone can develop a bell as wide as a human is tall, and tentacles that trail for over 100 feet in the abyss. Something about the deep ocean encourages growth on a scale that is difficult to comprehend when you are standing on the shore, looking out at the flat blue surface that hides this world. But why? Why should depth and size be connected? It seems counterintuitive. The deep ocean is a place of scarcity. There is no sunlight, so there are no plants, no algae, no seaweed, no phytoplankton. The entire food web of the abyss depends on the slow, drifting rain of organic particles that fall from the sunlit waters above. This rain is called marine snow. It is composed of dead plankton, fish scales, fecal matter, and fragments of organic material that slowly sink through the water column. By the time this material reaches the deep sea floor, most of its nutritional value has been stripped away by the organisms that live in the layers above. What remains is a thin, sparse dusting of food. A single square meter of the abyssal plain receives only about 1 or 2% of the food that falls on a square meter of the shallow ocean floor. By any reasonable logic, large animals should not be able to survive in such a food desert. Large bodies require large amounts of energy. Large creatures must eat frequently to maintain their size. The deep ocean should be a world of tiny things, of miniature shrimp and microscopic worms that have adapted to scarcity by becoming smaller. And yet, the opposite is true. The deeper you go, the larger some of them become. This is the mystery, and it is a mystery that has puzzled marine biologists since the first deep-sea dredging expeditions of the late 19th century hauled up creatures that no one had ever seen before. When the HMS Challenger expedition set sail in 1872, its mission was to explore the depths of the world's oceans. The scientists on board did not know what they would find. Many believed that below a certain depth, around 3,000 feet, the ocean would be completely devoid of life. The pressure, they argued, would be too great. The darkness would be too absolute. The cold would be too intense. But when they lowered their dredges and hauled them back up, they found a world teeming with life. And among that life were creatures of astonishing size. They brought up giant shrimps, giant worms, giant sea spiders whose leg spans could reach over a foot across. The expedition cataloged over 4,000 new species, and among them were the first documented examples of deep-sea gigantism. The scientists were baffled. They had no framework to explain what they were seeing. They simply recorded the measurements, sketched the specimens in their notebooks, and moved on to the next dredge. More than a century later, we still do not have a complete answer. There are theories, several of them, each with its own logic and its own limitations. But no single explanation has emerged as the definitive answer to the question of why things grow so large in the deep. And perhaps there is no single answer. Perhaps deep-sea gigantism is not one phenomenon, but several. driven by different forces in different groups of animals, all converging on the same strange outcome. Perhaps the giant isopod grows large for different reasons than the giant squid. Perhaps the giant jellyfish follows its own path to enormity. The deep ocean is not one environment, but many, layered on top of each other like the pages of a book, each depth zone with its own temperature, its own pressure, its own chemistry, its own ecology. And in each of these zones, different rules may apply. But before we descend into the details, before we meet the individual giants that haunt the abyss, we must understand the world they inhabit. Because deep-sea gigantism is not just about size. It is about the environment that makes size possible. And that environment is unlike anything we experience on the surface. The deep ocean is a place of extremes. It is cold beyond what most of us can imagine. Below about 3,000 feet, the temperature drops to around 4 degrees Celsius. That is just above freezing. It stays there, constant and unchanging, for thousands of feet more. There are no seasons in the deep sea. There is no day and no night. There is only the same cold, the same darkness, the same pressure, day after day, century after century, for millions of years. And the pressure is the thing that most defines the deep ocean. It is the force that shapes the bodies of the creatures that live there, that determines what can survive and what cannot. At the surface, we live under the weight of the atmosphere, about 14.7 pounds per square inch. We do not feel it because our bodies are adapted to it, because the pressure inside us matches the pressure outside. But descend into the ocean, and that balance changes. Every 10 meters you go down, the pressure increases by another atmosphere. At 1,000 meters, the pressure is 100 times greater than at the surface. At 4,000 meters, it is 400 times greater. At the bottom of the deepest trenches, over 10,000 meters down, the pressure is more than 1,000 times standard atmospheric pressure. To understand what that means, imagine a creature living in the deep sea. Imagine the force pressing on every square inch of its body. It is the equivalent of having a car sitting on every square inch of your skin. And yet life thrives there. It not only survives, but grows to sizes that seem impossible. The giant isopod can reach over 2 feet in length. It is a scavenger, crawling slowly across the seafloor, feeding on the carcasses of fish and whales that fall from above. It can go for long periods without food, storing energy in its body, waiting for the next meal to drift down from the surface. It moves slowly, conserving energy, living a life of extreme patience. This slowness, this extreme energy efficiency may be part of the answer. In the deep sea, where food is scarce and unpredictable, the creatures that succeed are not the fast ones. They are not the energetic ones. They are the ones that can wait. They are the ones that can survive on almost nothing. And there is a relationship between body size and metabolic efficiency that may explain why waiting and growing large go hand in hand. But the giant isopod is just the beginning. It is the gateway creature, the one that divers and submersible pilots most commonly encounter. It is the one that has become the mascot of deep-sea gigantism, the animal that appears in textbooks and documentaries as the prime example of this strange phenomenon. But there are others, far stranger and far larger, lurking in the deeper waters beyond. There is a creature that has eyes the size of dinner plates. There is a creature whose arms, if you could stretch them out, would be longer than a school bus. There is a creature that lives so deep and so slowly that it may live for 400 years, growing larger with each passing century. And there is a creature so rarely seen that it has been filmed alive only a handful of times in all of human history. Each of these animals is a testament to the power of the deep to reshape life in its own image. Each of them challenges our assumptions about what is possible in the natural world. So let us begin our descent. Let us leave the surface behind. The light will fade soon. The blue will deepen to indigo, then to violet, then to black. The temperature will drop. The pressure will build. And somewhere in that darkness, the giants are waiting. Some of them we know. Some of them we have only glimpsed. Some of them we have not yet discovered at all. The deep ocean is the largest living space on Earth. It covers more than 60% of the planet's surface and reaches depths of over 36,000 feet in its deepest trenches. And we have explored only a tiny fraction of it. We have mapped the surface of Mars in greater detail than we have mapped the floor of our own oceans. We have sent more human beings to the moon than to the deepest point of the sea. The giants of the deep live in a world that is, for all practical purposes, still unknown to us. This is the story of those giants. It is a story of science and mystery, of fact and theory, of what we know and what we have yet to learn. It is a story that begins with a simple observation and leads into some of the deepest questions about life on Earth. Why do things grow so large in the deep sea? What forces drive this strange and beautiful phenomenon? And what does it tell us about the nature of life itself? The answers are not simple. They are woven together from threads of ecology, physiology, evolution, and physics. They involve cold temperatures and slow metabolisms, scarce food and patient predators, ancient evolutionary histories, and recent adaptations to extreme environments. As we begin to untangle these threads, we will meet creatures that seem more like science fiction than reality. We will encounter a crustacean that looks like a prehistoric monster but is actually a gentle scavenger. We will meet a squid that fights sperm whales in the darkness, a squid so large that its tentacles are lined with sharp hooks that rotate like the blades of a circular saw. We will meet a fish that lives for centuries, growing slowly in the cold, dark waters of the Arctic deep. And we will encounter the strange and beautiful world of the gelatinous giants, creatures made almost entirely of water, whose bodies are so delicate that they dissolve into a shapeless mass when brought to the surface. But before we can understand the giants, we must understand the deep. We must understand what it means to live under thousands of feet of water. We must understand the pressure, the cold, the darkness, and the silence. Because these are not just conditions that the giants endure. These are the forces that shape them, that drive their evolution, that determine their size and their shape and their way of life. The deep sea is not just where they live. It is what made them what they are. So let us take a breath. Let us prepare for a long, slow descent. The surface world, with its light and warmth and noise, will soon be far behind us. Below us, the water darkens. The last rays of sunlight fade at around 1,000 meters. Below that, there is only the black. And in that black, there are eyes watching. There are giant claws reaching out from the sediment. There are tentacles drifting in the currents. There are creatures that have never seen the sun and never will. This is their world, and we are about to enter it. The giant isopod is waiting at the edge of the continental slope. It does not know we are coming. It does not care. It has been waiting for millions of years, crawling slowly across the sediment, eating what falls from above, growing larger with each molt of its segmented exoskeleton. It is a living fossil, a creature that has changed little since the time of the dinosaurs. And it is a symbol of something deeper, something that runs through the entire history of life in the deep sea. The deep sea does not make things larger because it is kind. It makes things larger because it is harsh. It makes things larger because the only way to survive in a world of scarcity and extreme pressure is to become slow, patient, and efficient. And in that world, larger is often better. But how much larger can they get? What are the limits of deep-sea gigantism? Is there a maximum size that even the most extreme conditions cannot exceed? Or could there be creatures in the deepest trenches that dwarf everything we have found so far? These are questions that scientists are still trying to answer. Every new expedition to the deep sea brings back new data, new specimens, new photographs of creatures that no human eye has ever seen before. And sometimes those photographs reveal something unexpected, something that challenges our assumptions about what lives in the abyss. As we go deeper, we will explore the evidence. We will look at the leading theories of deep-sea gigantism and the scientists who study them. We will examine the creatures themselves, from the familiar to the utterly alien. And we will try to understand why the deep sea, despite its scarcity and its hostility, produces some of the largest animals on Earth. It is a journey that will take us from the shallow continental shelves to the deepest ocean trenches, from the age of sail to the age of robotics, from the known to the unknown. And it begins here, in the quiet darkness, with a creature that looks like a giant woodlouse crawling across the mud. The giant isopod, Bathynomus giganteus, belongs to a group of crustaceans known as isopods. On land, the most familiar isopods are the woodlice, also known as pillbugs or roly-polies, those small gray creatures that curl into a ball when disturbed. There are over 10,000 species of isopods in the world, and most of them are small. A typical woodlouse measures about half an inch in length. It lives under rotting logs, in leaf litter, in damp basements, and in gardens. It is a humble creature, unremarkable, easily overlooked. But in the deep sea, the isopods have taken a different path. The giant isopod can reach lengths of over 20 inches and weigh nearly 4 pounds. It is not just a large version of a woodlouse. It is a woodlouse writ large, a creature that seems to belong to a different scale of existence altogether. The first giant isopod was described in 1879 by the French zoologist Alphonse Milne Edwards, who received specimens dredged from the Gulf of Mexico. He named it Bathynomus giganteus, which means deep-chested giant. The specimens he examined were impressive, but later discoveries would dwarf them. In 2010, a research expedition in the Gulf of Mexico captured a giant isopod measuring over 2.5 feet in length. The animal was photographed and released, but the image circulated widely on the internet, shocking people who had never imagined that such a creature existed. The comments were always the same. That looks like a monster. That looks like something from another planet. It lives in our oceans. And the response from marine biologists was always the same. Yes, it does, and it is not alone. The giant isopod is a benthic scavenger. It lives on the seafloor, crawling slowly across the sediment in search of food. Its diet consists primarily of dead fish, squid, and whale carcasses that fall from the surface. It has been observed feeding on the remains of larger animals that have sunk to the bottom, and it plays an important role in the deep-sea ecosystem as a cleanup crew, recycling organic material that would otherwise accumulate on the seafloor. But the giant isopod is also an opportunist. It will eat almost anything it can find, including living prey if it is slow enough to catch. Its mouth parts are adapted for cutting and tearing, and it can consume a surprising amount of food in a single feeding session. In fact, giant isopods have been known to eat so much that they become unable to move, lying on the seafloor for days while they digest their meal. This ability to consume large amounts of food at once and then survive for long periods without eating is a key adaptation to the deep-sea environment. Food in the abyss is unpredictable. A whale carcass may fall to the seafloor only once every few years in a given area. A giant isopod must be able to take advantage of such bonanzas when they occur and then survive the long intervals between them. Its slow metabolism allows it to do this. Its large body size may also help. Larger animals have more energy reserves, more storage capacity for fat and protein. They can afford to wait longer between meals. This is one of the leading theories for why deep-sea gigantism occurs. In an environment where food is scarce and unpredictable, being larger allows an animal to store more energy and survive longer periods of starvation. The giants of the deep are not gluttons. They are survivors. They are masters of patience. But the giant isopod is not the only crustacean that has grown large in the deep. There are giant amphipods, relatives of the tiny sand fleas that live on beaches around the world. In the deep sea, amphipods can reach lengths of over 12 inches. The largest known deep-sea amphipod is Alicella gigantea, which was first collected in the North Atlantic in the late 19th century and later found in the Pacific. A specimen measured over 13 inches in length, making it one of the largest amphipods ever recorded. For comparison, the amphipods that live in shallow waters are typically less than half an inch long. The difference in size is staggering, and it raises the same question. Why? There are also giant ostracods, another group of crustaceans. Ostracods are tiny, bivalve-like creatures that look like miniature clams. Most species are less than a millimeter in size, but in the deep sea, ostracods of the genus Gigantocyprus can reach over an inch in diameter. They are among the largest ostracods ever discovered, and they have another remarkable feature. They have enormous reflective eyes that are visible through their translucent shells. These eyes are adapted to detect the faint bioluminescent flashes of other deep-sea creatures. In the darkness of the abyss, where the only light is the light produced by living organisms, having large, sensitive eyes is a significant advantage. The giant ostracod uses its eyes to hunt for small prey and to avoid predators. Its large size may be linked to its need for these oversized visual organs. But again, the precise relationship between size and depth remains unclear. One of the most compelling observations about deep-sea gigantism is that it does not affect all groups of animals equally. Some groups show a clear trend toward larger size with increasing depth. Others show no trend at all, and still others show the opposite trend, becoming smaller as they go deeper. This suggests that gigantism is not a universal response to deep-sea conditions, but rather a specific adaptation that benefits certain types of animals in certain ecological niches. The challenge for scientists is to identify the factors that determine which groups become giants and which do not. The giant isopod has become an icon of deep-sea gigantism, but it is also something of a mystery. Despite being relatively common in certain parts of the deep ocean, scientists still do not fully understand its life cycle. How long does it live? How often does it reproduce? How fast does it grow? These basic questions remain unanswered for many deep-sea species, precisely because they are so difficult to study. You cannot simply put a giant isopod in a laboratory tank and observe it. The pressure and temperature conditions of the deep sea are difficult to replicate. And even if you could, the isopod's slow metabolism means that experiments would take years to yield results. The giant isopod lives on a different timescale from us. It operates in slow motion. This slow motion existence is one of the defining features of deep-sea life. Almost everything in the abyss happens more slowly than it does at the surface. Growth is slow. Reproduction is slow. Movement is slow. Even death is slow. The bodies of deep-sea creatures decompose very slowly because the cold temperatures inhibit bacterial activity. A whale carcass that falls to the deep seafloor may remain intact for decades, providing a long-term source of food for scavengers. Everything in the deep operates at a reduced speed, and this slowness may be connected to the phenomenon of gigantism in ways that scientists are only beginning to understand. One of the most intriguing theories connects deep-sea gigantism to the relationship between body size and metabolic rate. In general, larger animals have slower metabolic rates per unit of body mass than smaller animals. This is a well-established biological principle known as the metabolic scaling law, or Kleiber's law. A mouse burns energy much faster, relative to its size, than an elephant. This means that larger animals are more energy efficient. They need less food per pound of body weight than smaller animals. In the deep sea, where food is scarce, this efficiency may be a crucial advantage. If a deep-sea creature can grow large enough, it can reduce its relative energy requirements and survive on the sparse food that is available. But there is a catch. Growing large requires energy. A young giant isopod must eat enough to reach its adult size, and in the deep sea, that may take a very long time. The benefits of large size are only realized once the animal is fully grown. Getting there is the hard part. This may explain why deep-sea gigantism is most common in groups that have some other advantage, such as the ability to go for long periods without food, or the ability to exploit food sources that are not available to smaller competitors. The giant isopod can survive months or even years without a meal. It can afford to grow slowly because it can wait for the next food fall. Its patience allows it to reach sizes that would be impossible for a more active, faster metabolizing animal. Another theory focuses on temperature. The deep sea is extremely cold, and cold temperatures have a direct effect on the physiology of animals. In cold water, metabolic processes slow down. Cells divide more slowly. Growth rates decrease. But for some animals, this slowdown may actually allow them to grow larger over time. In cold environments, animals often reach sexual maturity later and continue growing for longer periods. This is known as the temperature size rule, and it has been observed in many groups of organisms, from fish to insects to crustaceans. In general, animals that develop in cold conditions grow more slowly, but reach a larger final size than those that develop in warm conditions. The deep sea, with its constant near-freezing temperatures, may be the ultimate expression of this rule. But temperature alone cannot explain all cases of deep-sea gigantism. Some deep-sea environments are not particularly cold. Hydrothermal vents, for example, can reach temperatures of over 400 degrees Celsius, and yet the animals that live there do not show the same trend toward gigantism. Similarly, some very cold environments at the surface, such as the polar oceans, produce large animals, but the pattern is different from the gigantism observed in the deep sea. There is something about the combination of cold, darkness, pressure, and food scarcity that creates the conditions for gigantism, and isolating the individual contributions of each factor is a difficult scientific challenge. The giant isopod represents one end of the crustacean gigantism spectrum, but there is another crustacean that takes gigantism to an even more extreme level. In the cold waters of the North Atlantic and the Arctic Ocean, there lives a creature known as the Greenland shark. It is not a crustacean, of course. It is a fish, a shark, and it is one of the largest predators on Earth. But it is also one of the slowest, and its connection to deep-sea gigantism is profound. The Greenland shark lives in deep, cold waters, often at depths of over 2,000 feet. It grows to lengths of over 20 feet and can weigh over a ton, and it lives for an extraordinarily long time. Recent studies using radiocarbon dating of the lenses of their eyes have shown that Greenland sharks can live for over 400 years. The oldest known individual was estimated to be around 500 years old. Some Greenland sharks may have been born before the Mayflower reached America. They are the longest living vertebrates on Earth. The Greenland shark grows at an incredibly slow rate, perhaps less than half an inch per year. It takes over a century for a Greenland shark to reach sexual maturity. Its entire life is conducted at a pace that is almost unimaginable to us. It moves slowly, breathes slowly, thinks slowly, grows slowly, and it reaches a size that is truly gigantic. This is deep-sea gigantism in its most extreme form. Not just large size for a crustacean, but large size for a vertebrate, a predator, a shark. The Greenland shark is a living reminder that the deep sea operates on timescales that are radically different from our own. But the Greenland shark is not the only giant fish in the deep. There are others, some even larger, some far stranger, and they all share a common pattern. They live in cold, deep water. They grow slowly. They live long lives, and they reach sizes that seem impossible given the scarcity of food in their environment. The deep sea, it seems, is a world of slow motion and enormous size, a world where patience is rewarded with gigantism, a world where the small become large and the slow become immortal. As we continue our descent, we will encounter creatures that take this pattern to even more extreme levels. We will meet squids that grow larger than buses. We will meet jellyfish whose tentacles stretch longer than blue whales. We will meet fish that live in the deepest trenches, surviving under pressures that would crush a submarine. And we will try to understand the forces that have shaped these remarkable animals. The deep sea is the largest habitat on Earth, and it is filled with giants. We are only beginning to learn their secrets. Of all the giants that live in the deep sea, none captures the imagination quite like the colossal squid. Its scientific name is Mesonicoteuthis hamiltoni, which translates roughly to middle-clawed squid of Hamilton. It is a name that hints at its most distinctive feature. While other large squid have tentacles lined with suckers, the colossal squid has tentacles lined with hooks. Each of its two long tentacles is armed with sharp, rotating hooks that can swivel like the blades of a circular saw. When a colossal squid catches prey, those hooks dig into flesh and do not let go. The suckers on its arms are also lined with tiny teeth, creating a grasping surface that is more like a bear trap than a squid arm. This is not a gentle creature. It is a predator built for violence in the darkness. The colossal squid lives in the Southern Ocean, surrounding Antarctica, at depths of between 3,000 and 6,000 feet. It is rarely seen alive. Most of what we know about it comes from specimens that have been caught in fishing nets or found in the stomachs of sperm whales. Sperm whales are the only natural predator of adult colossal squid, and the scars on the heads of sperm whales tell the story of epic battles fought in the deep. The whales dive to depths of over 3,000 feet to hunt the squid, and the squid fight back with their hooks and their powerful arms. The scars left behind can be over an inch wide, and they are found on the heads of almost every adult sperm whale in the Southern Ocean. These are the marks of a predator that refuses to go quietly. The colossal squid is the largest invertebrate on Earth. It is heavier than the more famous giant squid, Architeuthis ducks, although the giant squid may be slightly longer. The largest known colossal squid specimen was caught by a fishing vessel in the Ross Sea in 2007. It measured over 33 feet in length and weighed nearly 1,100 pounds. But scientists believe that larger specimens exist. The beaks of colossal squid found in the stomachs of sperm whales suggest that some individuals may reach lengths of over 45 feet. That is longer than a typical school bus. And those beaks, the hard parrot-like mouthparts of the squid, are another clue to its size and power. The beak of a large colossal squid is about the size of a grapefruit, with a sharp curved tip that can cut through the toughest fish flesh. It is a weapon that rivals the jaws of many large predators. The eyes of the colossal squid are the largest of any known animal. They can reach up to 11 inches in diameter, about the size of a dinner plate. These enormous eyes are adapted to detect the faint bioluminescent flashes of prey and predators in the darkness of the deep sea. In a world where light is rare and precious, having large eyes can mean the difference between finding food and starving. But the size of the colossal squid's eyes also presents a mystery. Some scientists have suggested that the eyes may be so large because the squid uses them not just to see bioluminescence but to detect the silhouettes of sperm whales approaching from above. Even in the dim light of the deep ocean, a sperm whale passing overhead would create a faint shadow, and a giant eye might be just sensitive enough to detect it. This theory, proposed by researchers at Duke University, suggests that the colossal squid's enormous eyes are an adaptation for predator detection rather than prey capture. It is a reminder that in the deep sea, even the largest predators must constantly watch for danger. The colossal squid is a deep-sea giant in the truest sense. It lives in waters that are among the most hostile on Earth. The temperature is near freezing. The pressure is crushing. The food is scarce. And yet the colossal squid thrives. It grows to enormous sizes. It lives a life of darkness and cold and violence. Its existence challenges our understanding of what is possible in the deep ocean. If a squid can grow to 45 feet in length in such an environment, what else might be down there? The discovery of the colossal squid is a relatively recent event in scientific history. Although the species was first described in 1925 from 2 arms found in the stomach of a sperm whale, it was not until the late 20th century that one-junged specimens were recovered. In 1981, a Russian trawler caught a large squid in the Ross Sea that was later identified as a colossal squid. In 2003, another specimen was caught, and in 2007, the largest specimen to date was captured. Each new discovery has added to our understanding of this remarkable animal, but much remains unknown. No one has ever observed a live colossal squid in its natural habitat. No one has filmed one swimming, hunting, or interacting with other creatures. We know it exists only from the bodies that have been brought to the surface, damaged and dying from the depths. This lack of direct observation is one of the great frustrations of deep-sea biology. We know that the colossal squid is out there, in the Southern Ocean, in the darkness. We know that it grows to enormous sizes. We know that it fights with sperm whales in the depths, but we have never seen it alive. We have only seen the aftermath of its existence. The scars on the whales, the beaks in their stomachs, the bodies in the nets. The colossal squid remains a ghost, a presence that we know is there but cannot see. This is the nature of deep-sea gigantism. It is a phenomenon that we can observe in fragments and pieces, but never fully comprehend. The animals are too large, too deep, too rare for us to study them properly. We are like astronomers trying to understand a distant planet by analyzing the light that reaches us from its atmosphere. We can infer much, but we can never see the surface directly. The deep sea is the last great frontier on Earth, and its giants are among the most elusive inhabitants of that frontier. The colossal squid is a master of the deep, a creature that has taken the principles of deep-sea gigantism to their most extreme conclusion. It has grown large, it has grown powerful, it has grown eyes that can see in the darkest waters, and it has grown hooks that can tear the flesh of a sperm whale. It is a testament to the power of the deep to shape life in unexpected ways. It is also a reminder of how much we have yet to learn. But the colossal squid is not the only giant cephalopod in the deep. There is another, more famous, and perhaps even stranger. The giant squid, Architeuthis dux, has haunted human imagination for centuries. It is the creature that gave rise to the legends of the Kraken, the sea monster that could drag entire ships beneath the waves. It is the animal that has been depicted in art and literature as a tentacled monster from the depths. And for most of human history, it was considered a myth. It was not until the late 19th century that the giant squid was finally proven to exist, when entire specimens washed ashore on the coast of Newfoundland. But even then, the mystery remained. The giant squid was a real animal, but no one had ever seen it alive in its natural habitat. It was a ghost that had left its body on the shore. It would take over 100 years before that changed. In 2004, a team of Japanese researchers, led by Tsunemi Kubodera, did what no one had done before. They photographed a live giant squid in its natural habitat at a depth of 3,000 feet in the waters off the Ogasawara Islands. The images were grainy and dark, but they were unmistakable. A giant squid, attracted by a bait line, approached the camera, its long tentacles trailing behind it. The photograph was published around the world and became an instant sensation. For the first time, humanity had seen the kraken in its own world. The image showed a creature that was both beautiful and alien. The giant squid's body was long and streamlined, its eyes were large and dark, and its tentacles were covered with suckers that glowed faintly in the light of the camera. The animal moved slowly, deliberately, as if it were dancing in the darkness. It was not a monster. It was a living creature, perfectly adapted to its environment, and the photograph captured something of its grace and mystery. Since that first photograph, there have been other sightings. In 2012, a joint team of Japanese and American researchers, including Tsunemi Kubodera and Edith Witter, captured the first video of a giant squid in its natural habitat off the Ogasawara Islands. In 2019, a team from the National Oceanic and Atmospheric Administration filmed a juvenile giant squid in the Gulf of Mexico. Each sighting has added to our knowledge, but the giant squid remains elusive. It is still one of the least understood large animals on the planet. The giant squid and the colossal squid are often confused with each other, but they are very different animals. The giant squid, Architeuthis, has longer tentacles and a more slender body. The colossal squid, Mesonychoteuthis, is heavier and more muscular, with hooks instead of suckers on its tentacles. The giant squid lives in temperate and tropical waters around the world, while the colossal squid is restricted to the cold waters of the Southern Ocean. They belong to different families, with the colossal squid classified in the family Cranchidae and the giant squid in Architeuthidae. And yet, both are examples of deep-sea gigantism. Both have taken the basic squid body plan and expanded it to extraordinary proportions. Both are evidence that the deep ocean can produce giants. But why the deep ocean should produce giant squid is still a matter of debate. Some scientists believe that giant squid evolved large size as a defense against predators, particularly sperm whales. A larger squid is harder to swallow and more capable of fighting back. Others believe that large size allows giant squid to exploit food resources that are unavailable to smaller squid, such as large fish and other deep-sea creatures. Still, others suggest that giant squid may simply be the result of a long evolutionary history in a stable environment, where the pressures that keep body sizes small at the surface are absent. As with all questions of deep-sea gigantism, the answer is likely to be complex and multifaceted. If the giant squid and the colossal squid represent one kind of deep-sea gigantism, the bigfin squid of the genus Magnapina represents something entirely different. It is not just large, it is bizarre. It is a creature that looks like it was designed by an imagination unconstrained by the laws of physics. Its arms, all 10 of them, are extraordinarily long and thin, and they extend from its body at sharp, elbow-like angles before trailing off into thin, whip-like filaments. The effect is unsettling. The squid looks like it is made of angles and threads, like a puppet whose strings have come loose. When it swims, its arms drift behind it like the tails of a kite, stretching out for lengths that seem impossible. The bigfin squid was first described in 1907 from a specimen found in the Atlantic Ocean, but it was so unusual that scientists were not sure what to make of it. It was not until the 1980s, when remotely operated vehicles began exploring the deep ocean, that the true nature of Magnapina became apparent. The first confirmed video footage of a live bigfin squid was captured in the early 2000s by remotely operated vehicles exploring the Gulf of Mexico for the oil and gas industry. The footage showed a creature with arms that appeared to be over 20 feet long, attached to a body that was only about 2 feet in length. The proportions were startling. It was as if a spider had been stretched out on a rack, its legs pulled to many times the length of its body. Since then, bigfin squid have been sighted in oceans around the world, from the Atlantic to the Pacific to the Indian Ocean. They appear to be widespread but rare. living at depths of between 3,000 and 15,000 feet. They are among the deepest living squids ever discovered, and they are among the strangest. The arms of a big-fin squid are not just long. They are covered with hundreds of tiny suckers, arranged in a pattern that allows the squid to capture prey by simply spreading its arms out like a net and waiting for something to bump into them. This is a passive hunting strategy, a way of catching food without expending much energy. In the deep sea, where energy is precious, passive strategies are often the most successful. The big-fin squid is a perfect example of how deep-sea gigantism can take forms that are completely unexpected. The giant isopod is a scaled-up version of a familiar animal. The colossal squid is a larger, more muscular version of a known squid type. But the big-fin squid is something else. Its arms are not just larger versions of normal squid arms. They are proportionally longer, thinner, and more flexible than those of any other squid. The gigantism of Magnapina is not uniform. It is concentrated in the arms, which are extended to extraordinary lengths, while the body remains relatively small. This suggests that the evolutionary pressures driving gigantism in the deep sea are not simply about getting bigger overall. They are about getting bigger in specific ways that confer specific advantages. Why would a squid evolve arms that are many times the length of its body? One possibility is that long arms allow the squid to capture prey from a greater distance without having to move its body. In the deep sea, where prey is scarce and the energy cost of movement is high, being able to catch food without chasing it is a significant advantage. The big-fin squid may simply spread its arms out like a web and drift through the water, catching whatever small creatures happen to swim into its reach. This would be an energy-efficient strategy for survival in a food-poor environment. Another possibility is that the long arms are used for sensing the environment. The suckers on the arms are covered with sensory cells that can detect chemical cues in the water. By extending its arms outward, the big-fin squid may be able to sample a larger volume of water for the scent of prey or predators. In the darkness of the deep sea, chemical sensing is often more important than vision. There is also the possibility that the long arms of the big-fin squid are used for defense. A predator that tries to attack a big-fin squid would have to contend with a tangle of thin, strong, and possibly sticky filaments that could wrap around its jaws and gills. The arms would be difficult to escape once they became entangled. This kind of passive defense is common in the deep sea, where the energy cost of active fighting is high. Better to be difficult to eat than to fight. The big-fin squid is one of the most rarely seen animals on Earth. It has been filmed alive only a handful of times, and each sighting raises new questions. How long do the arms actually get? The largest individuals have been estimated to have arms reaching over 26 feet in length, but this is based on limited video footage. There may be individuals with even longer arms, swimming in waters that no one has ever explored. The big-fin squid is a reminder that the deep sea is still full of surprises, that new discoveries are waiting in the darkness, and that the phenomenon of deep-sea gigantism may take forms that we cannot yet imagine. Another enigmatic cephalopod is the seven-arm octopus, Halophron atlanticus. Despite its name, the seven-arm octopus actually has 8 arms. The name comes from a peculiar feature of the males. One of their arms is modified into a specialized reproductive organ called a hectocotylus, and it is usually kept hidden in a pouch beneath the eye. To early scientists examining dead specimens, the male appeared to have only 7 arms. The seven-arm octopus is one of the largest octopuses in the world. Females can reach lengths of over 11 feet and weigh over 165 pounds. They are deep sea dwellers, living at depths of between 1,000 and 5,000 feet. And they are rarely seen. Most of what we know about them comes from specimens that have been caught in fishing nets or found in the stomachs of sperm whales. The seven-arm octopus is another example of deep-sea gigantism in the cephalopod lineage. It shares the same environment as the giant squid and the colossal squid, and it has evolved to similar proportions. But unlike the squids, the seven-arm octopus is a gelatinous animal. Its body is soft and watery, with little muscle mass. It drifts through the deep ocean, using its arms to capture small prey. Its gelatinous body is an adaptation to the deep sea. In the abyss, where food is scarce, it is more energy efficient to be soft and slow than to be fast and muscular. Gelatinous animals use less energy to maintain their bodies, and they can survive on less food. The seven-arm octopus has taken the path of soft gigantism, growing large without growing strong. This is a pattern that we will see again and again in the deep sea. There are two kinds of giants. There are the muscular giants, like the colossal squid, that grow large to become powerful predators. And there are the gelatinous giants, like the seven-arm octopus and the big-fin squid, that grow large without becoming strong. Both strategies are successful. Both allow animals to reach impressive sizes in an environment that seems to discourage size. And both raise the same fundamental question: why is it so common for deep-sea animals to become larger than their surface relatives? The answer may lie in the unique ecology of the deep ocean. At the surface, body size is constrained by many factors. Predation is intense, and being small allows animals to hide from predators. Competition is fierce, and being small allows animals to exploit small niches that larger animals cannot reach. Food is abundant but requires speed and agility to capture. In the deep sea, these constraints are relaxed. Predation is less intense because there are fewer predators overall. Competition is less fierce because the environment is less crowded. Food is scarce but falls slowly from above, and the animals that can wait for it and process it efficiently are the ones that succeed. In this world, being large is not a disadvantage. It is an advantage. Large animals can store more energy. They can survive longer between meals. They can range over larger areas in search of food. And they can better withstand the physical challenges of the deep sea environment, such as the intense pressure. But size alone is not enough. The deep sea also requires patience. The giants of the deep are not fast. They are not aggressive. They are slow, deliberate, and efficient. They have evolved to do more with less, and their gigantism is a reflection of that efficiency. In the deep sea, big is not always better, but for those animals that can manage it, big is often the key to survival. As we continue our descent, we will encounter more giants, each with its own unique strategy for surviving in the abyss. We will meet jellyfish that are longer than blue whales. We will meet fish that live for centuries. We will meet creatures that have abandoned nearly all of the characteristics that we associate with animal life, becoming simple bags of gelatinous tissue that drift through the darkness. And through all of these encounters, we will see the same pattern. The deep sea encourages growth. It rewards patience. And it produces giants that challenge our understanding of what life can be. The big-fin squid and the seven-arm octopus are two of the most enigmatic giants of the deep. They are rarely seen, poorly understood, and utterly fascinating. They remind us that the deep ocean is not just a place of darkness and cold. It is a place of wonder. It is a place where the rules of the surface no longer apply. And it is a place that still holds secrets that we have not yet begun to uncover. There is a creature in the deep sea that is longer than a blue whale. It has no brain. It has no heart. It has no bones, no blood, no organs that we would recognize as such. It is made almost entirely of water, more than 95% water, and the rest is a thin layer of cells that organize themselves into a shape that is both beautiful and alien. This creature is a siphonophore, and it may be the longest animal on Earth. The species Priadubia, which lives at depths of between 2,000 and 5,000 feet, has been measured at over 160 feet in length. That is longer than the largest blue whale, longer than any dinosaur that ever lived, and it is made of nothing more than water and jelly. Siphonophores are not single animals in the way that we normally think of animals. They are colonies of individual organisms called zooids that are connected to each other and function as a single unit. Each zooid has a specific role. Some are responsible for movement, propelling the colony through the water. Some are responsible for feeding, capturing prey with stinging tentacles. Some are responsible for reproduction. Together, the zooids form a single entity that can reach extraordinary lengths. The siphonophore is a living network, a distributed intelligence that drifts through the deep sea, trailing its stinging tentacles behind it like a fisherman's net. The size of siphonophores is another example of deep-sea gigantism, but it is a different kind of gigantism from the giant isopod or the colossal squid. Those animals are larger versions of familiar body plans. The siphonophore is a colony that has grown by adding more units. Its length is not a measure of individual growth, but of colonial expansion. And yet, the principle is the same. In the deep sea, where food is scarce and the energy cost of movement is high, it is advantageous to be long. A longer siphonophore can spread its tentacles over a larger volume of water, capturing more prey with less effort. It can drift through the darkness like a living net, catching whatever small creatures happen to swim into its reach. The lion's mane jellyfish, Cyanea capillata, is another gelatinous giant. It is the largest known species of jellyfish, with a bell diameter that can reach over 7 feet and tentacles that can trail for over 120 feet. The lion's mane jellyfish lives in the cold waters of the Arctic, North Atlantic, and North Pacific Oceans. It is a predator, using its stinging tentacles to capture small fish, crustaceans, and other jellyfish. Its size is a product of the cold waters it inhabits, following the temperature size rule that we discussed earlier. In cold water, jellyfish grow more slowly but reach larger sizes. The lion's mane jellyfish is the ultimate expression of this pattern. But there is another jellyfish that takes gigantism in a different direction. The deep-sea jellyfish Stygiomedusa gigantea is one of the largest jellyfish in the world, with a bell diameter of over 3 feet and 4 long, ribbon-like oral arms that can trail for over 20 feet. Unlike the lion's mane, which lives in cold surface waters, Stygiomedusa lives in the deep sea, at depths of between 2,000 and 5,000 feet. It has been sighted only about 100 times since it was first described in 1910. It is one of the rarest and least understood large animals on Earth. Its deep habitat and gelatinous body make it difficult to study. When it is brought to the surface, it dissolves into a shapeless mass, its delicate tissues unable to withstand the change in pressure and temperature. Stygiomedusa is a true deep-sea giant. It belongs to the family Ulmaridae, which includes the common moon jellyfish, but it has taken the basic jellyfish body plan and scaled it up to enormous proportions. Its 4 oral arms are broad and paddle-like, and they may be used to capture prey or to sense the environment. Very little is known about its behavior or ecology. It drifts through the deep ocean, a ghost made of light and water, and we know almost nothing about its life. Another remarkable jellyfish is the deep-sea crown jellyfish, Atolla wyville. It is not as large as Stygiomedusa, but it has a unique adaptation that may help explain the evolution of deep-sea gigantism in gelatinous animals. When threatened, Atolla wyville produces one of the most spectacular bioluminescent displays in the ocean. It releases a wave of blue light that travels across its bell, creating what scientists call a burglar alarm display. The idea is that the flash of light attracts the attention of a larger predator, which will then attack the animal that is threatening the jellyfish. It is a cry for help, a way of turning the tables on a predator, by calling in an even bigger one. This strategy only works if there are larger predators in the vicinity, and in the deep sea there are. The presence of large predators in the deep ocean may be one of the drivers of gelatinous gigantism. If you are a gelatinous animal that can be eaten by anything with a mouth, it pays to be too big to swallow. A Stygiomedusa with a 3-foot bell and 20-foot arms is a challenging meal for most predators. Its size is a defense. It is a way of saying, I am too large to bother with. And this defense may be one reason why gelatinous animals in the deep sea tend to be larger than their shallow water relatives. The deep sea is full of gelatinous giants. There are giant larvaceans, which build delicate houses of mucus that can be over 3 feet in diameter. There are giant pelagic sea cucumbers, which drift through the water column like transparent sausages. There are giant comb jellies which shimmer with iridescent light as they paddle through the darkness. Each of these animals has taken the basic body plan of its group and expanded it to proportions that seem impossible. And each of them has done so in the same environment, the cold, dark, food-poor waters of the deep sea. Why? Why does the deep sea produce so many gelatinous giants? One theory focuses on the metabolic advantages of gelatinous bodies. Gelatinous tissue requires very little energy to maintain. A jellyfish that is 95% water uses far less energy to sustain its body than a fish of the same size. In the deep sea, where food is scarce, being gelatinous is a survival strategy. You can grow large without needing to eat much. Your body is cheap to maintain. You can drift through the darkness waiting for food to come to you, and you can survive for long periods between meals. Gelatinous gigantism is a solution to the problem of scarcity. It allows animals to be big without being expensive. Another theory focuses on the mechanical properties of gelatinous bodies in the deep sea. Under high pressure, gelatinous tissue may be more resilient than muscular tissue. A jellyfish can withstand pressure changes that would crush a fish. Its body is incompressible, mostly water, and water does not compress easily. This means that gelatinous animals can move up and down through the water column without suffering the physiological stress that affects fish. They can live at extreme depths, where the pressure would make life impossible for most animals. And at those depths, they can grow to sizes that are unheard of in the surface world. The gelatinous giants of the deep sea are among the most mysterious animals on Earth. They are fragile, elusive, and poorly understood. They live in a world that we are only beginning to explore. And they are perfect examples of the strange and wonderful phenomenon of deep-sea gigantism. They remind us that the deep ocean is not just a place of darkness and cold. It is a place of beauty, of grace, of adaptations that we could never have imagined. As we drift deeper into the abyss, we encounter more of these gelatinous wonders. A siphonophore stretches across the water like a living ribbon, its tentacles pulsing with bioluminescent light. A stygiomedusa glides past, its bell expanding and contracting in a slow, hypnotic rhythm. A comb jelly shimmers with rainbow colors, each row of cilia catching the light and scattering it like a prism. These are the giants of the deep, not monsters but marvels, not horrors but wonders. They drift in the darkness, unseen by human eyes, living their quiet lives in the cold. We must now turn our attention to a different kind of deep-sea giant, not a crustacean, not a cephalopod, not a jellyfish, a fish, a shark, a creature that has lived in the cold, dark waters of the North Atlantic and the Arctic Ocean for millions of years, growing slowly, living long, and reaching sizes that rival the great white shark. This is the Greenland shark, Somniosus microcephalus. Its scientific name means sleepy one with a small head, and it lives up to its name. The Greenland shark is one of the slowest moving fish in the ocean. It cruises at a speed of less than 1 mile per hour. It rarely accelerates. It rarely changes direction. It simply drifts through the cold waters, conserving energy, waiting for opportunity. The Greenland shark is a true deep-sea giant. It grows to lengths of over 20 feet and can weigh over 2,000 pounds. Some unconfirmed reports suggest that individuals may reach over 24 feet in length. It is one of the largest predatory sharks in the world, comparable in size to the great white shark. But unlike the great white, which is a fast, warm-bodied predator of the surface waters, the Greenland shark is a slow, cold-bodied predator of the deep. It lives at depths of between 600 and 6,000 feet, though it is occasionally seen in shallower waters during the winter months. Its body temperature is only slightly above the freezing point of seawater. Its metabolism is incredibly slow. Its heart beats only a few times per minute. It is a creature that operates on geological timescales. Recent research has revealed something astonishing about the Greenland shark. It is the longest living vertebrate on Earth. In 2016, a team of scientists led by Julius Nielsen of the University of Copenhagen published a study in which they used radiocarbon dating to determine the ages of 28 female Greenland sharks. The results were startling. The oldest shark in the study was estimated to be between 272 and 512 years old, with a most likely age of around 392 years. Even the conservative estimate would make the Greenland shark the longest living vertebrate known to science. The oldest individual in the study may have been born around the year 1505, before the Protestant Reformation, before the discovery of the New World by European explorers, before the invention of the telescope. She has been swimming in the cold, dark waters of the North Atlantic for 5 centuries. How is this possible? How can a fish live for 500 years? The answer lies in the environment. The Greenland shark lives in water that is near freezing. Cold temperatures slow down every biological process. Cellular division slows, metabolism slows. The accumulation of cellular damage, which is the primary cause of aging, slows. In cold water, life operates at a reduced speed. The Greenland shark has taken this principle to its extreme. It grows at a rate of less than half an inch per year. It does not reach sexual maturity until it is over 100 years old. Its entire existence is conducted at a pace that is almost incomprehensible to us. This slowness is connected to the shark's size. The Greenland shark is large because it is old. It has had centuries to grow. Its gigantism is not the result of rapid growth, but of extended growth. It simply keeps growing, year after year, decade after decade, century after century. Its size is a measure of its age, and its age is a measure of the extreme cold in which it lives. This is a different kind of deep-sea gigantism from the giant isopod or the colossal squid. It is gigantism through longevity. It is the slow accumulation of size over time. But the Greenland shark's gigantism is also adaptive. Being large allows it to hunt larger prey. The Greenland shark feeds on fish, seals, and even scavenges the remains of polar bears. It is an apex predator in its environment, and its size gives it access to food sources that smaller predators cannot exploit. Its large body also allows it to store more energy, which is important in an environment where food can be scarce. The Greenland shark can go for months without eating, relying on its energy reserves to sustain it through lean periods. Its size is both a product of its environment and an adaptation to it. The Greenland shark is also a scavenger, feeding on the carcasses of whales and other large animals that sink to the seafloor. Its slow metabolism allows it to survive on these intermittent bonanzas, gorging itself when food is available and then fasting for months or even years. This ability to survive long periods without food is a common feature of deep-sea giants. It is one of the key adaptations that allows large size to evolve in a food-poor environment. There is another deep-sea shark that deserves mention here. The Pacific sleeper shark, Somniosus pacificus, is a close relative of the Greenland shark and shares many of its characteristics. It grows to similar sizes, lives at similar depths, and has a similar slow metabolism. It is found throughout the North Pacific Ocean, from Japan to Alaska to California. Like the Greenland shark, it is a deep-sea giant that has evolved to thrive in cold, dark waters. And like the Greenland shark, it remains poorly understood. We know that it exists, we know that it grows large, but we know very little about its life history, its behavior, or its ecology. The sleeper sharks are named for their sluggish, slow-moving lifestyle. They are not built for speed. They are built for endurance. They drift through the deep ocean, conserving energy, waiting for food to come to them. Their slow metabolism allows them to survive on a fraction of the food that a more active predator would require, and their large size allows them to dominate their environment, to be the top predators in a world where energy is scarce and patience is rewarded. The Greenland shark and the Pacific sleeper shark are not the only deep-sea fish that have grown large through slow growth and long life. There are others, such as the orange roughy, which can live for over 200 years and grow to over 2 feet in length. There is the Patagonian toothfish, which can live for over 50 years and grow to over 7 feet in length. There are deep-sea grenadiers and rat-tails that live for decades and grow to impressive sizes. Each of these fish has followed the same pattern. In the cold, food-poor waters of the deep sea, slow growth and long life are the keys to success. But there is a cost to this strategy. Slow-growing, long-lived animals are highly vulnerable to overfishing. It took centuries for a Greenland shark to reach its adult size. If it is caught by a fishing vessel, centuries of growth are lost in an instant. The population cannot recover quickly because the sharks take so long to reach sexual maturity. Many deep-sea fish populations have been severely depleted by fishing precisely because they grow so slowly and live so long. The deep sea is not a renewable resource in the way that shallow waters are. The giants of the deep are fragile. They are vulnerable. They are at risk. The Greenland shark represents one of the most extreme examples of deep-sea gigantism in vertebrates. It shows that gigantism can be achieved not through rapid growth, but through extraordinary longevity. It shows that the deep sea, with its cold temperatures and scarce food, favors animals that can wait. And it reminds us that the giants of the deep are not invulnerable. They are the products of millions of years of evolution, shaped by an environment that we are only beginning to understand. And they are disappearing in some cases before we have even had a chance to study them. As we descend further, the water grows darker and colder. The Greenland shark drifts below us, a shadow in the depths. It does not notice us. It does not care. It is following a scent, a faint chemical trail that leads to a whale carcass lying on the seafloor miles away. It will take days to reach it, but the shark is in no hurry. It has been waiting for centuries. It can wait a little longer. We have now met many of the giants of the deep: the giant isopod, the colossal squid, the bigfin squid, the siphonophore, the Stygia medusa, the Greenland shark. Each of these animals has its own unique story, its own evolutionary path to gigantism. But they all share something in common. They all live in the deep sea. And the deep sea has certain characteristics that seem to encourage large body size. The question is, what are those characteristics? How do they interact? And which of them is most important? The most obvious characteristic of the deep sea is its temperature. Below about 3,000 feet, the ocean is uniformly cold, hovering just above freezing. This cold temperature has a profound effect on the physiology of ectothermic animals, those that cannot regulate their own body temperature. In cold water, metabolic rates slow down. Chemical reactions happen more slowly. Cells divide more slowly. Growth rates decrease. But for many animals, slower growth leads to larger final size. This is known as the temperature size rule, and it has been observed in a wide range of organisms, from bacteria to fish to crustaceans. The basic idea is that cold temperatures delay maturity, allowing animals to continue growing for a longer period before they reach reproductive age. Because they mature later, they have more time to accumulate size. The temperature size rule is a well-established biological pattern, but it is not universal. Some animals show the opposite trend, becoming smaller in cold environments. And the relationship between temperature and size is complex, mediated by factors such as food availability, oxygen levels, and predation pressure. Nevertheless, the cold temperature of the deep sea is almost certainly one of the factors that drives deep-sea gigantism. It creates an environment where slow growth is the norm, and slow growth often leads to large size. But temperature alone cannot explain everything. For one thing, the deep sea is not uniformly cold everywhere. Hydrothermal vents can reach temperatures of over 400 degrees Celsius, and the animals that live near these vents do not show the same trend toward gigantism. For another, some of the largest deep-sea animals, such as the giant squid, live in waters that are not particularly cold. The giant squid has been found in tropical and temperate waters, where temperatures are much warmer than the near-freezing conditions of the abyss. Temperature is clearly not the only factor at work. Another important factor is metabolism. In general, larger animals have slower metabolic rates per unit of body mass than smaller animals. This is known as Kleiber's law, named after the biologist Max Kleiber, who first described the relationship in the 1930s. A mouse has a much higher metabolic rate per gram of body weight than an elephant. This means that larger animals are more energy efficient. They need less food per pound of body weight than smaller animals. In the deep sea, where food is scarce, this efficiency may be a crucial advantage. A giant isopod needs less food per ounce of its body than a small isopod. Its large size allows it to survive on the sparse resources of the abyss. But this leads to a paradox. To become large, an animal must first grow from a small size. Growing requires energy. A young giant isopod must eat enough to reach its adult size, and in the deep sea that may be difficult. The benefits of large size are only realized once the animal is fully grown. Getting there is the challenge. This paradox may explain why deep-sea gigantism is most common in groups that have some other adaptation that helps them survive the growth phase. The giant isopod can go for long periods without food, which helps it survive the lean years of its youth. The Greenland shark has a slow metabolism from birth, which reduces its energy requirements. The colossal squid is a predator with sharp hooks that can capture prey efficiently. Each giant has a strategy for getting through the difficult early years of life. There is another metabolic factor to consider. In cold water, the solubility of oxygen increases. This means that deep-sea waters are often rich in dissolved oxygen. For animals that rely on oxygen for metabolism, this may be another advantage of the deep-sea environment. With more oxygen available, animals can grow larger without outgrowing their oxygen supply. This is related to a concept known as the oxygen temperature hypothesis, which suggests that body size is limited by the ability of an animal to deliver enough oxygen to its tissues. In cold, oxygen-rich waters, this limit is higher, allowing animals to grow larger. The oxygen temperature hypothesis has been invoked to explain the large size of some polar animals, such as the lion's mane jellyfish and the Greenland shark. It may also explain why some deep-sea animals are larger than their shallow-water relatives. The deep sea is cold and well oxygenated, providing ideal conditions for large body size. But again, the evidence is mixed. Some deep-sea environments are low in oxygen, such as the oxygen minimum zones that occur at intermediate depths, and these environments do not seem to produce giants. The relationship between oxygen, temperature, and body size is complex, and scientists are still working to understand it. Another factor that may drive deep-sea gigantism is the scarcity of food. This seems counterintuitive. How can scarce food lead to large size? The answer lies in the relationship between body size and energy storage. Larger animals can store more energy in the form of fat and protein. They can survive longer periods of starvation. In the deep sea, where food falls are unpredictable and can be separated by months or years, the ability to store energy is crucial. A giant isopod can eat a large meal when food is available and then survive for months or even years on its energy reserves. A small isopod with less storage capacity would starve during the lean periods. Large size is an adaptation to food scarcity, but there is another way to think about this. If food is scarce, you might expect animals to become smaller, not larger. Smaller animals need less food overall. They can survive on smaller meals. This is a valid argument, and it explains why some deep-sea animals are tiny, but the animals that have taken the path of gigantism have found a different solution. Instead of reducing their food requirements by becoming small, they have increased their storage capacity by becoming large. They have solved the problem of scarcity through the strategy of feast and famine. Eat a lot when food is available. Survive on reserves when it is not. This strategy is only possible if food falls are large enough to support it. A giant isopod cannot survive on a few flakes of marine snow. It needs a large food source, such as a whale carcass or a large fish carcass. The deep sea, for all its scarcity, does have these large food falls. Whale carcasses in particular provide a massive input of energy to the deep sea floor. A single whale carcass can feed a community of scavengers for years. The giant isopod is one of the primary beneficiaries of these food falls. Its large size allows it to compete effectively for this resource, to eat its fill and store the energy for the lean times ahead. The Greenland shark follows a similar strategy. It feeds on large prey, such as seals and fish, and it can survive for months between meals. Its slow metabolism reduces its energy requirements, and its large size allows it to store energy efficiently. The Greenland shark is a master of the feast and famine strategy, a creature that has adapted to scarcity by becoming large, slow, and patient. These factors, temperature, metabolism, oxygen, food scarcity, do not operate in isolation. They interact with each other in complex ways. Cold temperatures slow metabolism, which reduces food requirements. Slow metabolism allows animals to survive longer between meals. Longer survival allows animals to grow larger. Larger animals can store more energy, which further extends their survival. It is a feedback loop, a cycle that reinforces itself over evolutionary time. The deep sea is not just a place where gigantism happens. It is a place that actively promotes gigantism, that creates the conditions for large size to evolve and persist. But there are other factors as well. We have not yet discussed the role of pressure. We have not yet discussed the role of predation. We have not yet discussed the role of competition. These factors are equally important, and they may help explain why some groups of animals become giants while others do not. We will now consider these additional factors and try to assemble a more complete picture of the forces that drive deep-sea gigantism. The puzzle is complex, but the pieces are beginning to come together. We have considered temperature, metabolism, oxygen, and food scarcity as drivers of deep-sea gigantism. But there are other factors that may be equally important. One of these is pressure. The pressure in the deep sea is immense, reaching over 1,000 times atmospheric pressure in the deepest trenches. How does this pressure affect body size? The answer is not straightforward, but there are several hypotheses. One idea is that high pressure favors larger body size because larger animals have a lower surface area to volume ratio. In a high-pressure environment, the forces acting on an animal's body are distributed over its surface. A larger animal has proportionally less surface area relative to its volume, which means that the pressure forces are more evenly distributed. This may make larger animals better able to withstand the mechanical stresses of the deep sea. A giant isopod, with its thick, segmented armor, may be better equipped to handle pressure than a small, thin-bodied isopod. Another idea is that high pressure affects the biochemistry of proteins and cellular membranes. Deep-sea animals have evolved specialized adaptations to counteract these effects, such as the production of pressure-resistant proteins and the incorporation of unsaturated fatty acids into their cell membranes. These adaptations may be energetically expensive, and larger animals may be better able to afford them. A large body can devote more resources to maintaining pressure-resistant biochemistry than a small body. This could give larger animals an advantage in the high-pressure environment of the deep sea. But there is also evidence that pressure limits body size in some groups. The deepest living fish, for example, are generally small. The Mariana snailfish, which lives at depths of over 26,000 feet, measures only about 4 inches in length. It is a tiny fish that has adapted to extreme pressure by becoming small and gelatinous. This suggests that pressure does not always favor large size. It may favor large size in some groups and small size in others, depending on the specific adaptations required to survive at depth. Another important factor is predation. In the deep sea, predation pressure is generally lower than at the surface. There are fewer predators overall, and the predators that do exist are often slow-moving and specialized. This reduced predation pressure may allow deep-sea animals to grow larger than their surface relatives. At the surface, being small is often an advantage because it allows animals to hide from predators. A small fish can conceal itself among rocks and corals. A small crustacean can burrow into the sediment. But in the deep sea, where there are few places to hide and few predators to hide from, the advantage of small size is reduced. Animals can grow larger without attracting the attention of predators. This may explain why some deep-sea animals have abandoned the typical predator avoidance strategies of their surface relatives. The giant isopod does not hide. It crawls openly across the seafloor, its armor providing protection against any predator that might try to eat it. The colossal squid does not flee from sperm whales. It fights them, using its hooks and powerful arms. The Greenland shark is a predator itself, and it has no natural enemies other than humans and possibly other Greenland sharks. In the deep sea, the rules of predator-prey interactions are different. Size is not a liability, it is an asset. Competition is another factor that may drive deep-sea gigantism. In the deep sea, competition for resources is intense, but it is a different kind of competition from what we see at the surface. At the surface, competition is often about speed. The fastest predator catches the prey. The fastest prey escapes the predator. But in the deep sea, speed is less important. The competition is about patience and efficiency. The animal that can survive the longest without food is the one that will succeed. The animal that can process food most efficiently is the one that will grow largest. In this kind of competition, size is an advantage. Larger animals can store more energy, and they can wait longer between meals. There is also the factor of Bergmann's rule, an ecological principle that states that within a broadly distributed taxonomic group, populations and species of larger size are found in colder environments, while populations and species of smaller size are found in warmer regions. This rule was first proposed by the German biologist Carl Bergmann in 1847, and it has been observed in many groups of mammals and birds. The rule is usually explained by the relationship between body size and heat conservation. Larger animals have a lower surface area to volume ratio, which means they lose heat more slowly. In cold environments, being large helps animals retain body heat. Bergmann's rule applies primarily to endothermic animals, those that generate their own body heat, but it may also apply to ectothermic animals, such as fish and crustaceans, through different mechanisms. In cold water, the tissues of ectothermic animals have different properties than in warm water. They may be less permeable to water and ions, which could affect the relationship between body size and physiological function. Some researchers have suggested that Bergmann's rule, mediated through cold temperature, may be one of the drivers of deep-sea gigantism. But Bergmann's rule has its critics. Some scientists argue that the pattern is not as consistent as it appears, and that other factors, such as food availability and predation, are more important. The debate over Bergmann's rule continues, but it is clear that temperature plays some role in determining body size in many groups of animals. So where does this leave us? We have multiple theories, each with some evidence to support it. Temperature, metabolism, oxygen, food scarcity, pressure, predation, competition, Bergmann's rule. All of these factors may contribute to deep-sea gigantism in different ways and in different groups of animals. The challenge is to determine which factors are most important and how they interact. Some scientists believe that the key factor is the combination of cold temperature and low food availability. Cold temperature slows metabolism, reducing energy requirements. Low food availability means that animals must be efficient in their use of energy. Large size through the metabolic scaling law provides efficiency. Animals that are large need less food per unit of body weight than animals that are small. In the cold, food-poor deep sea, large size is an adaptation that allows animals to survive on limited resources. Other scientists emphasize the role of predation. They argue that the deep sea is a refuge from the intense predation pressure of the surface waters. At the surface, animals are under constant threat from predators, and being small allows them to hide. In the deep sea, predation is less intense, and the pressure to remain small is relaxed. Animals can grow larger without being eaten. This release from predation may be the primary driver of deep-sea gigantism. Still, other scientists focus on the role of dissolved oxygen. They note that cold water holds more oxygen than warm water, and that oxygen availability can limit body size in some animals. In the oxygen-rich waters of the deep sea, animals can grow larger without outgrowing their oxygen supply. This may be particularly important for animals that rely on diffusion to obtain oxygen, such as many gelatinous species. And there are scientists who argue that deep-sea gigantism is not a single phenomenon but several, each with its own cause. The giant isopod may be large because of food scarcity and metabolic efficiency. The colossal squid may be large because of predation pressure from sperm whales. The Greenland shark may be large because of its extreme longevity in cold water. The bigfin squid may have long arms because of the advantages of passive feeding. Each giant may have its own story, its own path to gigantism. This is the most likely explanation. Deep-sea gigantism is not a single phenomenon with a single cause. It is a collection of phenomena, each driven by different factors in different groups of animals. The deep sea is not one environment, but many. It is a mosaic of habitats, each with its own temperature, pressure, chemistry, and ecology. And in each of these habitats, different forces shape the evolution of body size. What works for a crustacean in the abyssal plain may not work for a squid in the mesopelagic zone. What drives gigantism in a shark may not drive gigantism in a jellyfish. The deep sea is complex, and its giants are complex too. As we continue our descent, we will see more evidence of this complexity. We will encounter giants that have evolved in response to specific pressures, and we will see how the same environment can produce different kinds of gigantism in different groups. The deep sea is a laboratory of evolution, and the giants are its most spectacular experiments. The deep-sea giants we have met so far are alive today. They swim, crawl, and drift through the darkness of the present-day ocean. But the phenomenon of deep-sea gigantism is not limited to the modern era. It has a long history, stretching back millions of years. The deep ocean has produced giants throughout geological time, and some of the most spectacular examples of gigantism in Earth's history were deep-sea animals. The most famous of these ancient giants is Megalodon, the giant shark that lived from about 23 million to 3.6 million years ago. Megalodon is often depicted as a monstrous version of the great white shark, but the scientific evidence suggests that it was a different animal altogether. It belonged to a different lineage, the Odontoceti, which are now extinct. Megalodon was one of the largest and most powerful predators ever to have lived. Estimates of its size vary, but most researchers agree that it reached lengths of over 50 feet, with some individuals possibly exceeding 60 feet. Its teeth, which are the most common fossil remains, are triangular and serrated, measuring over 7 inches in length. They are larger than a human hand. Megalodon is not typically classified as a deep-sea animal, but there is evidence that it may have spent much of its time in deep water. Its fossils have been found in sedimentary rocks that were deposited in deep ocean environments, and its teeth are often recovered from deep-sea sediments by dredging operations. Some researchers have suggested that Megalodon may have been a deep-sea predator, hunting large prey in the open ocean and occasionally venturing into shallower waters to feed. This would make it one of the most extreme examples of deep-sea gigantism in the history of life. But Megalodon was not the only giant predator of the ancient seas. There was also Livyatan melvillei, a giant sperm whale that lived during the same period as Megalodon. Livyatan was named after the biblical sea monster Leviathan and the author of Moby Dick, Herman Melville. It was enormous, with a skull length of over 9 feet and total body length estimated at over 50 feet. Unlike modern sperm whales, which have teeth only in their lower jaws, Leviathan had massive teeth in both its upper and lower jaws. The largest teeth were over a foot long and over 4 inches in diameter. They are among the largest teeth ever found. Leviathan was a predator that could have competed with Megalodon for food in the ancient oceans. These ancient giants raise an interesting question. Were they examples of deep-sea gigantism, or were they something else? Megalodon and Leviathan lived in a world that was warmer than the present-day ocean. The climate was different, and the ocean ecosystems were structured differently. But the same principles may have applied. Large size in the ocean, whether in the past or the present, is often associated with cold, deep water and the efficient use of resources. The ancient giants may have followed the same rules as the modern ones. There were also giant deep-sea reptiles in the age of dinosaurs. The mosasaurs were a group of giant marine lizards that lived during the late Cretaceous period. Some species reached lengths of over 50 feet. They were apex predators in the ancient oceans, feeding on fish, turtles, and other marine reptiles. Mosasaurs are often thought of as surface-dwelling animals, but some species may have been adapted to deeper waters. Their large eyes and streamlined bodies suggest that they were capable of diving to significant depths in search of prey. The ichthyosaurs, another group of marine reptiles, also reached impressive sizes. Some species, such as Shawnosaurus popularis, reached lengths of over 65 feet. These were among the largest animals ever to live in the ocean, rivaling the size of modern whales. Ichthyosaurs were fast, streamlined predators that hunted fish and squid in the open ocean. They may have dived to considerable depths, although direct evidence of their diving behavior is lacking. All of these ancient giants, from Megalodon to Leviathan to the mosasaurs and ichthyosaurs, share certain characteristics with modern deep-sea giants. They were large. They were predators. They lived in the ocean. And they may have spent significant portions of their lives in deep water. But were they driven to large size by the same factors that drive gigantism today? It is difficult to say with certainty. The fossil record provides only limited information about the behavior and ecology of extinct animals. We can infer some things from their anatomy, but we cannot observe them in their natural habitat. What we can say is that the deep ocean has been producing giants for millions of years. It is not a recent phenomenon. The trend toward large size in deep-sea animals has deep evolutionary roots, and it may be related to the same factors that we have been discussing: cold temperature, food scarcity, metabolic efficiency, reduced predation. These factors have been present in the deep ocean for most of Earth's history, and they have shaped the evolution of life in the abyss. But there is a difference between ancient and modern deep-sea gigantism. The ancient giants were, for the most part, surface-dwelling animals that may have spent time in deep water. The modern giants, by contrast, are true deep-sea animals that live their entire lives in the abyss. The giant isopod does not venture to the surface. The colossal squid does not bask in the sun. These animals are adapted to a life that is permanently in the dark. They are the product of millions of years of evolution in the deep sea, and they represent a different kind of gigantism from the ancient surface-dwelling giants. This difference may be important. It may explain why the modern deep-sea giants are generally smaller than the ancient surface-dwelling giants. Megalodon was over 50 feet long. The colossal squid is maybe 45 feet. The Greenland shark is 20 feet. The giant isopod is 2 feet. The modern deep-sea giants are large, but they are not as large as the giants of the past. This may be because the deep sea imposes constraints on size that the surface does not. The pressure, the cold, the scarcity of food, all of these factors limit how large an animal can grow. The ancient surface-dwelling giants did not face these constraints. They lived in a world of light and warmth, where food was abundant and the only limit to size was competition with other predators. But there is another possibility. Perhaps the modern deep-sea giants are not the end of the story. Perhaps there are giants in the deep sea that we have not yet discovered. The deep ocean is vast, and we have explored only a tiny fraction of it. We have mapped less than 20% of the seafloor in detail. There are deep-sea trenches that have never been visited. There are underwater mountain ranges that have never been surveyed. There are vast abyssal plains that stretch for thousands of miles, and we have no idea what lives there. It is entirely possible that there are animals in the deep sea that are larger than anything we have found so far. The discovery of the colossal squid in the 20th century is a reminder that the deep sea can still surprise us. This enormous animal, the largest invertebrate on Earth, was unknown to science until less than 100 years ago. It was not discovered through a systematic search. It was found by accident, in the stomach of a sperm whale. How many other giants are waiting to be discovered? How many more colossal squids, giant isopods, and deep-sea sharks are swimming in waters that we have never explored? The search for deep-sea giants continues. Every year, new expeditions venture into the abyss, carrying cameras, robots, and submersibles. Every year, they return with images of creatures that have never been seen before. And sometimes, those images reveal something large, something unexpected, something that reminds us that the deep sea is still a place of mystery and wonder. In 2021, researchers from the Monterey Bay Aquarium Research Institute exploring the depths of the Pacific Ocean captured stunning footage of a giant phantom jellyfish, Stygiomedusa gigantea, with a bell over 3 feet wide and arms trailing for over 20 feet. The footage was released to the public and quickly went viral, with millions of people watching the graceful alien creature drift through the darkness. It was a reminder that the giants of the deep are still out there, still waiting to be seen, still waiting to be understood. The deep sea is the last great wilderness on Earth. It covers more than half of the planet's surface, and it contains some of the largest animals on Earth. But we have only begun to explore it. The giants of the deep are not relics of the past. They are living animals, swimming in the darkness, growing large in a world that we are only beginning to understand. As we have seen, the deep sea produces giants, but it does not produce unlimited giants. There are limits to how large a deep-sea animal can grow, and those limits are imposed by the physics and biology of the environment. Understanding these limits is important if we want to understand the phenomenon of deep-sea gigantism in its full context. One obvious limit is food. Even with the metabolic advantages of large size, a deep-sea animal must still consume enough energy to sustain its body. The deep sea is a food-poor environment, and the food that does exist is distributed unevenly. A colossal squid must eat enough to maintain a body that weighs over 1,000 pounds. It must find and capture enough prey to support its metabolism, even if that metabolism is slow. There must be enough food in the Southern Ocean to support a population of colossal squids, and that sets a limit on how large the squids can grow. If they were much larger, they would simply starve. Another limit is pressure. While some deep-sea animals are adapted to high pressure, there is a limit to how much pressure any organism can withstand. The proteins that make up an animal's body can only be stabilized to a certain extent. The cell membranes can only be reinforced so much. Beyond a certain depth, even the most pressure-adapted animal would begin to suffer structural damage. The deepest fish ever recorded, a Mariana snailfish, was filmed at a depth of over 26,000 feet. But it was a relatively small fish, about 11 inches in length. It is possible that the extreme pressure at the bottom of the deepest trenches limits the size of animals that can live there. The deeper you go, the smaller the animals may become. There is also the limit of oxygen. While the deep sea is generally well oxygenated, some parts of it are not. Oxygen minimum zones occur at intermediate depths in many parts of the world, where the decomposition of organic matter consumes oxygen faster than it can be replenished. In these zones, oxygen levels can drop to near zero, making it impossible for most animals to survive. Animals that live in or near oxygen minimum zones are typically small and have specialized adaptations for extracting oxygen from low oxygen water. The presence of oxygen minimum zones may set limits on the distribution of deep-sea giants. There is also the limit of reproduction. Deep-sea giants tend to have slow life histories. They grow slowly, mature late, and reproduce infrequently. This slow reproductive rate makes them vulnerable to population declines. If the environment changes, if food becomes scarcer or predation increases, a population of giant isopods or colossal squids may not be able to recover quickly. This vulnerability may limit the distribution and abundance of deep-sea giants. They can only survive in environments that are stable enough to support their slow life histories. But within these limits, there is still room for discovery. The deep sea is vast, and we have explored only a tiny fraction of it. New species are discovered every year, and some of them are large. In 2020, a new species of giant isopod was described from the deep waters of the Indian Ocean near Indonesia. It was named Bathynomus raksasa, and it measured over 1.5 feet in length. In 2014, a new species of deep-sea jellyfish was discovered in the Gulf of Mexico. It had a bell over 3 feet wide. Earlier in 2008, a new species of deep-sea squid was described from specimens collected in the Pacific Ocean. It was given the name Asperiteuthis mangoldii, and it was notable for its large size and unusual morphology. The discoveries keep coming. The deep sea is not a static environment. It is changing, and those changes may affect deep sea gigantism. The ocean is warming, and as it warms, the cold, deep waters that the giants depend on may become less cold. This could have a significant impact on the temperature-dependent processes that drive gigantism. If the deep ocean warms, the metabolic rates of deep-sea animals will increase. They will need more food. Their growth rates may change. Their maximum sizes may decrease. The giants of the deep may become smaller in a warmer world. There is also the impact of fishing. Many deep-sea giants are caught as bycatch in commercial fisheries. The Greenland shark is often caught in trawls and long lines. The giant isopod is sometimes caught in traps set for crabs and lobsters. The colossal squid is occasionally caught in fishing nets. These catches, even if they are not targeted, can have a significant impact on populations of slow-growing, long-lived animals. A single Greenland shark that is caught and killed represents centuries of growth that will not be replaced for generations. The giants of the deep are vulnerable to human activities, and their future is uncertain. There is also the impact of pollution. The deep sea is not immune to the effects of human activity. Plastic debris has been found at the bottom of the deepest trenches. Chemical pollutants have been detected in the tissues of deep-sea animals. The noise from shipping and industrial activities can travel for thousands of miles through the deep sound channel, disrupting the behavior of animals that rely on sound for communication and navigation. The deep sea is not the pristine wilderness that we imagine it to be. It is increasingly affected by human activities, and the giants that live there are feeling the effects. Despite these challenges, the deep sea remains one of the most fascinating and mysterious places on Earth. Its giants are among the most remarkable animals on the planet, and they deserve our attention and our protection. They are not monsters. They are not horrors. They are living creatures, adapted to a world that is radically different from our own. They are the products of millions of years of evolution, shaped by the cold, the pressure, the darkness, and the scarcity of the deep. And they are a reminder that there is still wonder in the world, still mystery, still places that we have not yet explored. The giant isopod crawls across the seafloor, its segmented armor gleaming in the light of a submersible. The colossal squid drifts in the darkness of the Southern Ocean, its hooks ready to seize any prey that comes within reach. The bigfin squid spreads its impossibly long arms like a net, waiting for food to bump into them. The Stygiomedusa pulses its bell, trailing its ribbon-like arms through the water. The Greenland shark swims slowly, its ancient body carrying it through waters that it has known for centuries. These are the giants of the deep. They are real. They exist in the depths right now, each living its own slow story. We have descended far now. The surface is a memory. The light is gone. The warmth is gone. There is only the cold and the dark and the weight of the water above. We have traveled through a world that is alien to us, a world of giants that grow large in the absence of light. We have seen the isopod, the squid, the jellyfish, the shark. We have witnessed the strange and beautiful ways that life adapts to the abyss. And we have asked the question that drives all exploration. Why? Why do things grow so large in the deep sea? We have considered the theories: temperature, metabolism, food scarcity, pressure, predation, oxygen, Bergmann's rule, Kleiber's law. Each theory has its merits. Each theory has its limitations. The answer, we have learned, is not simple. It is not one thing. It is many things, woven together in ways that we are only beginning to understand. The deep sea is a world of trade-offs. To live there, an animal must make compromises. It must give up speed for efficiency. It must give up activity for patience. It must give up the light for the dark. And in return, it may grow large. It may live long. It may become a giant. But the price of gigantism is a slow life. A life lived at a reduced pace. A life of waiting and conserving and enduring. The giant isopod waits. It crawls across the sediment, searching for the next carcass to fall from above. It may wait months. It may wait years. But it does not mind. It was built to wait. Its slow metabolism allows it to survive the intervals between meals. Its large body stores energy for the lean times. It is a creature of patience, and patience is the currency of the deep. The colossal squid waits. It drifts in the cold waters of the Southern Ocean, its hooks ready, its eyes scanning the darkness for the silhouette of a sperm whale or the flash of bioluminescent prey. It may not encounter food for weeks. It may not encounter a mate for years. But it does not mind. It was built to wait. Its enormous eyes allow it to see in the dark. Its powerful arms allow it to capture prey when it comes. It is a creature of patience, and patience is the currency of the deep. The Greenland shark waits. It swims slowly through the cold Arctic waters, growing at a rate of less than half an inch per year. It will take over a century to reach maturity. It will live for 400 years or more. It does not rush. It does not hurry. It simply drifts, conserving energy, waiting for the next opportunity to feed. It is a creature of patience, and patience is the currency of the deep. The deep sea rewards patience. It rewards efficiency. It rewards the animals that can do more with less. And those animals, the ones that have mastered the art of patience, are the ones that grow large. They are the giants of the abyss. They are the isopods and the squids and the jellyfish and the sharks. They are the ones that have found a way to thrive in a world that seems designed to discourage life. We are not like them. We are creatures of the surface, of light and warmth and speed. We move fast. We live fast. We burn through energy at a rate that would be unsustainable in the deep sea. We could not survive there. Our bodies would be crushed by the pressure. Our cells would fail in the cold. Our minds would break in the darkness. The deep sea is not for us. It belongs to the giants, and perhaps that is why we find them so fascinating. They are a reminder that there is another way to live, a slower way, a more patient way, a way that does not require constant movement and constant consumption. The giants of the deep have found a path that we cannot follow, but we can admire it. We can marvel at it. We can let it quiet our restless minds as we drift toward sleep. The lights of the submersible fade as we ascend. The darkness returns. The water grows lighter. The blue deepens to indigo, to violet, to the pale green of the surface. We break the surface. We feel the warmth of the sun on our faces. We hear the sounds of the world above. The journey is over, but the memory of the deep remains. The image of the giants drifting in the darkness stays with us. We have glimpsed the giants of the abyss. We have seen their strange shapes in the darkness, and we have learned that the deep sea is not a void. It is not empty. It is full of life, full of wonder, full of mystery, and it is full of giants. They are down there right now as we sit in the warmth and the light. They are swimming in the darkness, crawling across the sediment, drifting in the currents. They are living their slow, patient lives in a world that we can barely imagine. And somewhere, in a part of the deep ocean that no one has ever visited, there may be giants that we have not yet discovered. Creatures larger than anything we have found so far. Creatures that have evolved in isolation for millions of years, untouched by human eyes. The deep sea is vast, and it keeps its secrets well. But every so often, it reveals one. A new species. A new giant. A new reminder that there is still wonder in the world. The deep sea is a place of darkness, but it is not a place of death. It is a place of life. Life that has adapted to the most extreme conditions on Earth. Life that has found a way to thrive where we thought nothing could survive. Life that grows large in the absence of light. The giants of the deep are a testament to the resilience of life, to its ability to adapt, to its endless capacity for surprise. They are the giants of the deep, and they will be there long after we are gone. But there is another creature we must meet before our journey ends, a creature that does not live in the abyssal depths but is connected to them by its size and its mystery. A creature that has been seen by sailors for centuries and called a sea serpent. A creature that is, in fact, a fish, the longest bony fish in the world. The oarfish. The oarfish, Regalecus glesni, is a fish of extraordinary proportions. It can reach lengths of up to 36 feet, making it the longest bony fish alive today, with unconfirmed reports of even larger individuals. Its body is ribbon-like, compressed laterally, and covered with silvery skin that shimmers like mercury in the light. On its head, it has a crest of bright red spines that resemble a crown. Its eyes are large and dark, adapted for seeing in the dim light of the mesopelagic zone, where it spends most of its life. The oarfish lives at depths of between 600 and 3,000 feet, though it occasionally ventures into shallower waters. And when it does, it often makes news. The oarfish is believed to be the source of many sea serpent legends. When a long, ribbon-like body with a red crest appears at the surface, it is easy to imagine a monster. The oarfish swims with an undulating motion, its body rippling like a serpent through the water. Its large eyes and gaping mouth add to the impression of a creature from the depths. For centuries, sailors returning from long voyages told tales of encountering sea serpents, and many of those tales may have been inspired by encounters with oarfish. But the oarfish is not a monster. It is a gentle giant, a filter feeder that consumes small crustaceans and plankton by straining them from the water with its gill rakers. It has only small teeth, unsuited for biting prey. It has no aggressive instincts. It is a creature of grace and beauty, not of violence. And it is another example of the strange and wonderful gigantism that occurs in the deep sea. The oarfish is not a true deep-sea fish in the sense that it does not live on the seafloor. It lives in the mesopelagic zone, the twilight zone of the ocean, where some light still penetrates but not enough for photosynthesis. This is a world of transition, a zone where the rules of the surface begin to break down, and the rules of the deep begin to take hold. And in this zone, the oarfish has grown to extraordinary lengths. Why does the oarfish grow so long? The answer may be related to its feeding strategy. The oarfish is a filter feeder, and a longer body allows it to process more water for the small particles of food that it consumes. A longer body also makes the oarfish more difficult for predators to eat. A 50-foot ribbon of muscle and bone is not an easy meal for most predators. The oarfish's size may be a defense against the sharks, seals, and other predators that hunt in the mesopelagic zone. The oarfish is rarely seen alive in its natural habitat. Most of what we know about it comes from specimens that have washed ashore, sick or dying, or from occasional encounters by submersibles and remotely operated vehicles. These encounters are always special, always memorable. To see an oarfish swimming in its natural environment is to witness one of the most remarkable sights in the ocean. In 2010, a team of researchers from the University of Louisiana at Lafayette captured video of an oarfish in the Gulf of Mexico. The fish was swimming vertically, with its head pointing upward and its body undulating gently. This vertical orientation is typical of oarfish and may be related to their feeding behavior. By swimming vertically, the oarfish can scan a larger volume of water for prey, using its large eyes to detect the silhouettes of small crustaceans against the dim light filtering from above. The video was a rare and valuable glimpse into the life of this mysterious giant. The oarfish is a reminder that deep-sea gigantism is not confined to the abyssal plains and trenches. It occurs throughout the deep ocean, in all its zones and habitats. The mesopelagic zone, the bathypelagic zone, the abyssopelagic zone, the hadal zone, each of these regions has its own giants, adapted to its own conditions. The oarfish is the giant of the twilight zone. The colossal squid is the giant of the Southern Ocean deep. The Greenland shark is the giant of the Arctic deep. The giant isopod is the giant of the continental slope. Each giant has its own realm, its own territory, its own place in the darkness. The oarfish also reminds us that deep-sea gigantism is not always about being heavy and muscular. Sometimes it is about being long and thin. The oarfish has achieved gigantism through length rather than mass. It is a different kind of giant, a giant of extension rather than bulk. And this may be an adaptation to the specific conditions of the mesopelagic zone, where the ability to process large volumes of water for scarce food is more important than the ability to capture and subdue large prey. The oarfish is also known as the king of herrings, a name that reflects its impressive size and the regal crest on its head. There are also deep-sea ribbonfish, which are smaller relatives and still impressive, reaching lengths of over 8 feet. These fish share the oarfish's ribbon-like body shape and its preference for deep water. They are part of a family of fish that have taken the path of length over mass, growing long and thin in the darkness of the deep. The oarfish is a living legend, a creature that has inspired myths and stories for centuries. It is also a scientific mystery, an animal that we know very little about, despite its enormous size. How long does it live? How does it reproduce? How does it find food in the vast darkness of the mesopelagic zone? These questions remain unanswered, waiting for the next generation of deep-sea explorers to solve. The oarfish represents yet another facet of the phenomenon of deep-sea gigantism. It shows that the deep ocean can produce giants in many forms, from the short and armored to the long and ribbon-like. It shows that the rules of size in the deep sea are different from the rules of size at the surface. And it shows that there is still much to learn about the creatures that live in the darkness below. But the giants of the deep are not limited to animals that we can see with the naked eye. There are giants in the deep sea that are invisible to us, giants that are made of a single cell. These are the xenophyophores, giant single-celled organisms that live on the deep seafloor. Xenophyophores are foraminifera, a group of amoeba-like organisms that build complex shells called tests. Most foraminifera are microscopic, smaller than a grain of sand, but xenophyophores can reach sizes of over 4 inches in diameter. They are among the largest single-celled organisms on Earth. Xenophyophores were first discovered in the late 19th century during the Challenger expedition. They were found in deep-sea sediments from around the world, living at depths of between 1,000 and 30,000 feet. They are particularly abundant in the abyssal plains of the Pacific Ocean, where they form dense mats on the seafloor. Their shells are made of accumulated particles from the sediment, glued together with organic cement. The shells can take many forms, from simple spheres to elaborate branching structures that resemble miniature trees. The size of xenophyophores is a mystery. Why would a single-celled organism grow to such enormous proportions? One theory is that their large size allows them to capture more food. Xenophyophores feed by extending thin strands of cytoplasm, called pseudopodia, through the openings in their shells. These pseudopodia trap bacteria and other organic particles from the surrounding sediment and water. A larger shell means more surface area for pseudopodia, which means more food can be captured. In the food-poor environment of the deep sea, being large may allow xenophyophores to feed more efficiently. Another theory is that the large size of xenophyophores is a defense against predators. In the deep sea, there are many small animals that feed on organic particles and the microorganisms that live in the sediment. A xenophyophore that is 4 inches across is too large for most of these predators to swallow. Its size protects it from being eaten. This is the same logic that drives gigantism in jellyfish and other gelatinous animals. Being too big to swallow is a powerful defense in the deep sea. Xenophyophores also play an important role in the deep sea ecosystem. Their shells provide habitat for other small animals, creating microenvironments on the otherwise featureless seafloor. The spaces within and around xenophyophore shells are home to a diverse community of small crustaceans, worms, and other organisms. The xenophyophores themselves are also a source of food for some deep-sea animals, such as sea cucumbers and starfish. They are a key part of the abyssal ecosystem, despite their simple structure. The gigantism of xenophyophores is a reminder that deep-sea gigantism is not confined to complex animals. It can occur at any level of biological organization, from the simplest single-celled organisms to the most complex vertebrates. The deep sea seems to encourage large size in all forms of life, regardless of their evolutionary complexity. There are other single-celled giants in the deep sea as well. The giant amoeba Gromia spherica was discovered in 2000 on the seafloor off the coast of the Bahamas. It is a spherical organism that can reach over 1.5 inches in diameter. Like xenophyophores, it is a single cell that has grown to an enormous size. It moves slowly across the seafloor, leaving behind distinctive trails that have been found in the fossil record dating back hundreds of millions of years. The giant sea spider, Colossendias, is another example of deep-sea gigantism in a group that is usually small. Sea spiders are marine arthropods that are related to spiders and horseshoe crabs. Most species are small, with leg spans of less than an inch. But in the deep sea, sea spiders can reach leg spans of over 20 inches. The giant sea spider Colossendias colossea has a leg span of over 2 feet. It lives at depths of between 3,000 and 10,000 feet, crawling slowly across the seafloor in search of food. Giant sea spiders are predators, feeding on soft-bodied animals such as sea anemones, jellyfish, and sponges. They use a long proboscis to suck the fluids from their prey. Their long legs allow them to cover large areas of the seafloor in search of food, and their large size may protect them from predators. Like the giant isopod, the giant sea spider is a scaled-up version of a familiar body plan, a creature that has taken the basic sea spider design and expanded it to impressive proportions. The giant tube worm, Riftia pachyptila, is another deep-sea giant that deserves mention. Tube worms live at hydrothermal vents, where they form dense colonies around the chimneys of superheated water. They can grow to over 8 feet in length with a diameter of over 1.5 inches. They have no mouth, no gut, and no anus. They are among the most unusual animals on the planet. The giant tube worm's gigantism is made possible by its symbiotic relationship with bacteria. The bacteria live inside the tube worm's body, where they convert the sulfur compounds from the vent fluids into organic carbon that the worm can use as food. This symbiotic relationship allows the tube worm to grow to enormous sizes without needing to eat. It is an extreme example of how deep-sea gigantism can be driven by unusual energy sources. The giant tube worm lives in one of the most extreme environments on Earth. Hydrothermal vents are places where superheated water, rich in sulfur and other minerals, blasts out of the seafloor at temperatures of over 400 degrees Celsius. The water is toxic, acidic, and under immense pressure. And yet, the tube worms thrive. They grow to enormous sizes. They live in dense colonies that cover the vent chimneys like a living blanket. They are another testament to the power of the deep to produce life in the most unlikely places. There are also giant clams in the deep sea, though they are not as large as their shallow water relatives. The deep-sea giant clam, Calyptogena magnifica, lives at hydrothermal vents and cold seeps, where it grows to lengths of over 8 inches. It is a filter feeder, using its gills to extract bacteria and organic particles from the water. Its size is modest compared to the giant clams of tropical reefs, but it is still impressive for a deep-sea animal. What all of these creatures have in common is that they have taken advantage of the unique conditions of the deep sea to grow larger than their surface relatives. Whether through slow metabolism, reduced predation, unusual food sources, or simple longevity, they have found a path to gigantism that works in their specific environment. And they remind us that the deep sea is not a barren wasteland. It is a world of giants, from the smallest single-celled organism to the largest squid. The more we explore the deep sea, the more giants we find. Each expedition brings back new discoveries, new species, new examples of life growing large in the darkness. The deep sea is the largest living space on Earth, and it is filled with creatures that we have only begun to understand. The phenomenon of deep-sea gigantism is one of the most fascinating mysteries in biology, and we are only beginning to unravel its secrets. What will the future hold for the giants of the deep? Will they continue to thrive in the cold, dark waters that they call home? Or will changes in the ocean, driven by human activity, threaten their existence? These are questions that scientists are beginning to ask, and the answers are not reassuring. The deep ocean is warming. As the planet heats up due to climate change, the cold waters of the abyss are slowly increasing in temperature. This warming may have a direct impact on deep-sea gigantism. If the water temperature rises, the metabolic rates of deep-sea animals will increase. They will need more food to sustain their bodies. But food in the deep sea is already scarce. An increase in metabolic demand could lead to starvation, especially for the largest animals, which require the most energy overall. The warming of the deep ocean could also affect the oxygen content of the water. Warm water holds less dissolved oxygen than cold water. As the deep sea warms, it may become less oxygenated. This could limit the maximum size that deep sea animals can achieve, since oxygen availability is one of the factors that constrains body size. The giants of the deep may become smaller in a warmer, less oxygenated ocean. There is also the threat of ocean acidification. As the ocean absorbs more carbon dioxide from the atmosphere, it becomes more acidic. This acidification can affect the ability of many marine animals to build their shells and skeletons. For deep-sea animals that rely on calcium carbonate structures, such as the shells of xenophyophores and the tests of foraminifera, acidification could be devastating. If the shells of these organisms dissolve, the entire deep-sea ecosystem could be affected. The giants of the deep also face direct threats from human activities. Fishing, shipping, mining, and pollution all take a toll on deep-sea ecosystems. The Greenland shark is caught as bycatch in fisheries. The giant isopod is sometimes harvested for scientific study or for the aquarium trade. The colossal squid is caught in fishing nets. These direct impacts, combined with the indirect impacts of climate change, create an uncertain future for the giants of the deep. But there is reason for hope. The deep sea is vast, and many parts of it remain untouched by human activities. There are still places where the giants can thrive, where the cold, dark waters are undisturbed. Marine protected areas have been established in some parts of the deep ocean, providing sanctuaries for deep-sea life. And there is growing awareness of the importance of the deep sea, both for its own sake and for the health of the planet as a whole. The future of deep-sea gigantism will depend on the choices that we make today. If we continue to exploit the deep ocean without regard for its inhabitants, the giants will suffer. If we take steps to protect the deep sea, to reduce our impact on it, the giants may continue to thrive for centuries to come. The Greenland shark that was born in the year 1500 is still swimming in the North Atlantic today. It has survived 5 centuries of human history. Whether it survives the next 5 centuries depends on us. There is also the exciting possibility of discovering new giants. The deep sea is the largest unexplored region on Earth. We have mapped less than 20% of the seafloor in any detail. There are deep sea trenches, mountain ranges, and abyssal plains that have never been visited by human eyes. It is entirely possible that there are animals in these unexplored regions that are larger than anything we have found so far. Consider the following. The colossal squid was only confirmed to exist in the early 20th century. The first footage of a live giant squid was captured in 2004. The big fin squid was not seen alive until the 1980s. New species of deep-sea jellyfish are discovered every year. The deep sea is still revealing its secrets, and some of those secrets may be large. Imagine a squid that is larger than the colossal squid. Imagine a jellyfish with a bell wider than a house. Imagine a fish that rivals megalodon in size, living in the unexplored depths of the Pacific. These are not fantasies. They are possibilities. The deep sea is vast enough and unexplored enough that such creatures could exist. We simply do not know. The search for deep-sea giants continues. New technologies are being developed that will allow us to explore deeper, longer, and more effectively. Remotely operated vehicles, autonomous underwater vehicles, and advanced sonar systems are opening up the deep sea to exploration in ways that were unimaginable a generation ago. Every year, we learn more about the creatures that live in the darkness. And every year, we find something new and unexpected. The giants of the deep are not just objects of scientific curiosity. They are symbols of the mystery and wonder of the natural world. They remind us that there are still places on Earth that we have not fully explored, still creatures that we have not fully understood. In a world that can sometimes feel small and familiar, the deep sea offers a reminder of the vastness and strangeness of life on our planet. From the giant isopod to the colossal squid, from the bigfin squid to the stygiomedusa, from the Greenland shark to the oarfish, from the single-celled xenophyophore to the giant tube worm. These are the giants of the deep. They are real. They are living. They are swimming, crawling, and drifting in the darkness of the abyss, right now, as we sit here in the light and warmth of the surface world. And somewhere, in a part of the deep ocean that no one has ever visited, there may be other giants, creatures that we have not yet imagined. Animals that have evolved in isolation for millions of years, untouched by human knowledge. The deep sea keeps its secrets well, but every so often it reveals one. A new giant, a new mystery, a new reminder that the world is still full of wonder. So the next time you look out at the ocean, remember what lies beneath. The darkness, the cold, the pressure, and the giants. They are down there, living their slow, patient lives in a world that we can barely imagine. They have been there for millions of years. They will be there long after we are gone. The giants of the deep, waiting in the darkness, always waiting. There is another dimension to the story of deep-sea gigantism that we have not fully explored. It is the connection between the deep sea and the possibility of life beyond Earth. In our solar system, there are moons that may harbor oceans beneath their icy crusts. Europa, a moon of Jupiter, is believed to have a global subsurface ocean of liquid water, kept warm by tidal heating from Jupiter's gravity. Enceladus, a moon of Saturn, has geysers that shoot water vapor into space, revealing the presence of a liquid ocean beneath its frozen surface. These oceans may be similar to the deep sea on Earth. They are dark, they are cold, they are under pressure, and they may contain life. If life exists in the subsurface oceans of Europa or Enceladus, it would almost certainly be microbial. The conditions are harsh, the energy sources are limited, and the ecosystems would be simple. But could larger forms of life evolve in those oceans? Could there be giants in the deep seas of other worlds? The answer depends on the same factors that drive deep-sea gigantism on Earth: temperature, food availability, oxygen, predation, pressure. If the subsurface oceans of icy moons are cold, as they likely are, then any life that exists there would have slow metabolisms. Slow metabolism could lead to large size, as it does in the deep sea on Earth. If food is scarce, as it likely would be, then large size could be advantageous for energy storage. If predation is limited, as it might be in a simple ecosystem, then the pressure to remain small would be reduced. The same conditions that produce giants in Earth's deep sea could produce giants in the oceans of other worlds. The giant tube worm, Riftia pachyptila, provides a model for what extraterrestrial life might look like. It lives in an environment that is completely dark, under extreme pressure, and powered by chemical energy rather than sunlight. Its symbiotic bacteria convert sulfur compounds into organic matter, providing the tube worm with all the food it needs. This is a chemosynthetic ecosystem, an ecosystem that does not depend on the sun. If life exists on Europa or Enceladus, it would likely be chemosynthetic, powered by chemical reactions between water and rock. And if chemosynthetic life can produce giants on Earth, it could produce giants on other worlds. The discovery of hydrothermal vent ecosystems in 1977 revolutionized our understanding of where life can exist. Before that discovery, scientists believed that all life on Earth ultimately depended on sunlight. The vents proved that life could thrive in complete darkness, powered by chemical energy from the Earth's interior. This discovery opened up the possibility that life could exist in other dark, chemically rich environments, such as the subsurface oceans of icy moons. The giants of the deep sea are not just a biological curiosity. They are a proof of concept. They show that large, complex life can evolve in environments that are completely isolated from the sun. They show that the deep sea, with its cold, darkness, and pressure, is not a barrier to life, but a cradle for it. And they suggest that if we ever explore the oceans of Europa or Enceladus, we may find giants there as well. But there is also a cautionary note. The giants of Earth's deep sea are vulnerable. They are slow-growing, long-lived, and slow to reproduce. They are easily disrupted by changes in their environment. If the subsurface oceans of icy moons contain life, that life would be even more vulnerable. It would be isolated, fragile, and potentially unique. We would need to approach it with care and respect. The connection between deep-sea gigantism and astrobiology is a reminder that the deep sea is not just a place of wonder on Earth. It is a window into the possibilities of life elsewhere in the universe. Every giant isopod, every colossal squid, every Greenland shark is a data point in the larger question of where life can exist and what forms it can take. The deep sea is our best laboratory for understanding the potential for life in the cosmos. As we continue to explore the deep sea on Earth, we are also preparing for the exploration of other oceans in the solar system. The technologies that we develop for deep sea exploration, the remotely operated vehicles, the autonomous underwater vehicles, the pressure-resistant cameras and sensors, will be the same technologies that we use to explore the oceans of Europa and Enceladus. The lessons that we learn about life in the deep sea will be the lessons that we apply to the search for life elsewhere. The giants of the deep are messengers from a world that is both alien and familiar. They show us what life can become when it adapts to extreme conditions. They show us that the universe may be filled with life, in forms that we cannot yet imagine. And they remind us that the greatest discoveries are still ahead of us, waiting in the darkness, waiting in the deep. So as we prepare to leave this world of giants, let us carry with us a sense of wonder. The deep sea is not a place that we can easily visit. It is not a place that we can ever truly know. But it is a place that exists right now beneath the surface of our own planet. And it is filled with giants. Giants that grow large in the absence of light. Giants that live for centuries. Giants that fight sperm whales in the darkness. giants that are made of nothing but water and patience. These are the giants of the deep, and they will be there, waiting in the darkness, for as long as the ocean exists. The story of deep-sea gigantism is also the story of human exploration. Every giant that we have met in this journey was discovered by someone, somewhere, at some point in history. The giant isopod was described in 1879 by Alphonse Milne Edwards. The colossal squid was first identified from 2 arms found in a sperm whale's stomach in 1925. The bigfin squid was first seen alive in 1988. The Greenland shark's extraordinary longevity was discovered in 2016. Each of these discoveries was made possible by the courage and curiosity of explorers who were willing to venture into the unknown. The history of deep-sea exploration is a history of technological innovation. In the 19th century, explorers used dredges and trawls to haul up samples from the depths. These were crude instruments, but they were effective. The Challenger expedition, which sailed from 1872 to 1876, used dredges to collect samples from depths of over 4,000 meters. The expedition discovered over 4,000 new species, many of which showed signs of deep-sea gigantism. The giant isopod was one of these discoveries. The giant sea spider was another. In the 20th century, new technologies opened up new possibilities. The development of the bathysphere, a tethered submersible, allowed humans to descend into the deep sea for the first time. In 1934, William Beebe and Otis Barton descended to a depth of over 3,000 feet in the bathysphere, observing deep-sea life directly for the first time. Beebe described seeing giant shrimps, strange fish, and other creatures that no human eye had ever seen before. His accounts were met with skepticism by some scientists who doubted that such large creatures could exist at such depths. But time proved Beebe right. The development of the bathyscaphe in the 1950s allowed humans to reach the deepest parts of the ocean. In 1960, Jacques Piccard and Don Walsh descended to the Challenger Deep in the bathyscaphe Trieste, reaching a depth of over 35,000 feet. Their descent was a triumph of engineering and courage, and it proved that human beings could reach the deepest place on Earth. But it also revealed how little we knew about the life that lived there. The development of remotely operated vehicles and autonomous underwater vehicles in the late 20th century revolutionized deep-sea exploration. These machines could stay underwater for hours or days, exploring areas that were too dangerous for human divers. They could carry cameras, sensors, and sampling equipment, allowing scientists to observe deep-sea life in its natural habitat for the first time. The first footage of a live bigfin squid was captured by a remotely operated vehicle in the Gulf of Mexico in 1988. The first footage of a live giant squid was captured by a team using a submersible and a bait line in 2004. These discoveries were made possible by technology that did not exist a generation earlier. Today, deep-sea exploration is more advanced than ever. New submersibles, such as the Chinese Fendouzhe and the American Limiting Factor, can reach the deepest parts of the ocean. New sonar systems can map the seafloor in unprecedented detail. New DNA sequencing techniques can identify species from water samples without ever seeing the animal itself. The tools of exploration are more powerful than ever, and they are revealing new giants every year. But the deep sea is vast, and exploration is slow. It would take hundreds of years to explore the entire deep ocean with current technology. Most of the deep sea remains unseen, unmapped, and unknown. The giants that we have discovered are just a small sample of what is out there. The giant isopod, the colossal squid, the Greenland shark, these are the giants that we know. There are almost certainly others that we do not. The search for deep-sea giants is not just a scientific endeavor, it is a human endeavor. It is driven by the same curiosity that drives all exploration, the desire to know what lies beyond the horizon. The deep sea is the last horizon on Earth, the last frontier, and it is filled with giants. Every expedition to the deep sea carries the possibility of discovery. Every dive of a submersible, every deployment of a remotely operated vehicle, every drop of a camera system could reveal something new. A new species, a new giant, a new piece of the puzzle of deep-sea gigantism. The explorers who venture into the deep sea are following in the footsteps of the Challenger scientists, of William Beebe, of Jacques Piccard, and Don Walsh. They are continuing the tradition of discovery that has revealed the wonders of the deep. The giants of the deep are not just animals or biological curiosities. They are symbols of the unknown. They represent the vastness of the ocean and the limits of human knowledge. Every time we discover a new giant, we are reminded of how much we have yet to learn. Every time we see a footage of a giant squid or a bigfin squid, we are reminded that the deep sea is still a place of mystery and wonder. The story of deep sea gigantism is not complete. It may never be complete. The deep sea is too large, too deep, too complex for us to ever fully understand. But that is part of its appeal. The mystery is what draws us to it. The unknown is what drives us to explore. The giants are what keep us coming back, again and again, to the darkness of the abyss. So let us continue to explore. Let us continue to descend into the darkness, to push the limits of our technology and our courage, to seek out the giants that live in the depths. Let us continue to ask the question that has driven this entire journey. Why do things grow so large in the deep sea? And let us be content with the knowledge that we may never have a complete answer. Some mysteries are meant to remain mysteries. Some secrets are meant to remain hidden. The deep sea is one of those secrets, and its giants are the keepers of that secret. There is another aspect of deep sea gigantism that we must consider. It is the role of the dead. The deep sea is a world of scavengers, and the largest scavengers are the giants. The giant isopod, the Greenland shark, the colossal squid, all of them depend to some extent on the carcasses of dead animals that fall from the surface. These carcasses, known as food falls, are the lifeline of the deep sea. They are the reason that giants can exist in a world of scarcity. The most important food falls in the deep sea are whale carcasses. When a whale dies, its body sinks to the seafloor, carrying with it an enormous amount of organic material. A single blue whale carcass can weigh over 100 tons. When it reaches the seafloor, it creates an oasis of life in the desert of the abyss. The carcass attracts scavengers from miles around. Giant isopods, sleeper sharks, hagfish, and other deep-sea animals converge on the carcass to feed. For years, sometimes decades, the carcass provides a source of food for the deep-sea community. The study of whale falls is a relatively new field in deep-sea biology. The first natural whale fall was discovered in 1987 off the coast of California at a depth of over 4,000 feet beneath the surface. Since then, dozens of whale falls have been studied, and each one has revealed new insights into the ecology of the deep sea. The carcass goes through several stages of decomposition. First, the soft tissues are consumed by mobile scavengers like giant isopods and sleeper sharks. Then the bones are colonized by specialized worms and bacteria that break down the lipids stored in the bone marrow. Finally, the remnants of the bones become a habitat for deep-sea corals and other suspension feeders. A whale fall can support a community of deep-sea life for decades. The giant isopod is one of the primary beneficiaries of whale falls. Its large size allows it to compete effectively for access to the carcass. It can consume large amounts of tissue in a single feeding session, storing the energy for the lean times ahead. Without whale falls, the giant isopod would not be able to survive in the deep sea. The food would be too scarce, the intervals between meals too long. Whale falls are the reason that giant isopods can exist. The Greenland shark also benefits from whale falls. Its slow metabolism allows it to survive on the intermittent food that whale carcasses provide. It can gorge itself on the carcass for days or weeks, then fast for months while it waits for the next food fall to occur. The Greenland shark's gigantism is made possible by the occasional bonanzas of whale carcasses and other large food falls. There are other types of food falls as well. Large fish carcasses, such as tuna and swordfish, can provide significant inputs of food to the deep sea. Squid carcasses are also important, especially in areas where squid are abundant. Even the carcasses of terrestrial animals, such as deer and cattle, can reach the deep sea floor in areas where rivers carry them out to sea. Each food fall creates a temporary oasis of life in the desert of the abyss. The study of food falls has revealed that the deep sea is not as food poor as we once thought. While the overall flux of organic material to the sea floor is low, it is concentrated in these occasional bonanzas. The giants of the deep have evolved to take advantage of these bonanzas. They have become large so that they can store more energy. They have become slow so that they can survive longer between meals. They have become patient so that they can wait for the next food fall to occur. This is one of the key insights of deep-sea gigantism research. The giants are not anomalies. They are not exceptions to the rules of the deep sea. They are the logical outcome of those rules. In a world where food is scarce and unpredictable, the animals that succeed are the ones that can wait. And the ones that can wait are the ones that are large, slow, and efficient. The giants of the deep are not a mystery. They are a solution. They are the solution that evolution has found to the problem of living in the abyss. The deep sea is a harsh world. It is cold. It is dark. It is under immense pressure. Food is scarce. Life is difficult. And yet, life persists. Life adapts. Life grows. And sometimes, life grows to enormous proportions. The giants of the deep are a testament to the resilience of life, to its ability to find a way even in the most extreme conditions. They are an inspiration. They are a wonder. And they are a reminder that the natural world is full of surprises, full of beauty, full of mystery. We have met many of the giants of the deep. We have learned their stories. We have asked the question of why they grow so large. And we have found that the answer is complex, multifaceted, and still incomplete. But that is the nature of science. The answers are never final. The questions are never fully resolved. There is always more to learn, more to discover, more to understand. The deep sea is vast. Its secrets are many. Its giants are waiting. And we will keep exploring, keep descending, keep seeking, because that is what we do. We are explorers. We are curious. We are driven to know what lies beyond. And the deep sea, with its darkness and its cold and its giants, will always call us back. There is one more depth zone that we have not yet visited, the Hadal Zone, the deepest part of the ocean, the trenches that plunge to over 36,000 feet below the surface. This is the most extreme environment on Earth. The pressure is over 1,000 times atmospheric pressure. The temperature is just above freezing. No sunlight penetrates. And yet, life exists here too. And some of that life is surprisingly large. The Hadal Zone was once thought to be devoid of life. The pressure, scientists believed, would be too great for any organism to withstand. But the first explorations of the deep trenches in the 1950s and 1960s revealed a different story. They found fish. They found shrimp. They found sea cucumbers. They found life in abundance where none was expected. And some of that life was larger than expected. The Hadal snailfish, Pseudoliparis swirae, lives at depths of over 26,000 feet in the Mariana Trench. It is a modest fish, about 11 inches in length, but its presence at such depths is remarkable. It is the deepest living fish ever discovered. Its body is gelatinous and translucent, adapted to the extreme pressure of the Hadal Zone. It feeds on small crustaceans that live in the trench sediments, but there are larger animals in the Hadal Zone as well. Giant amphipods, relatives of the small sand fleas, have been found in the deepest trenches. The amphipod Alicella gigantea can reach lengths of over 12 inches. It is one of the largest amphipods ever discovered, and it has been found at depths of nearly 20,000 feet. Its large size may be an adaptation to the scarcity of food in the Hadal Zone. Like the giant isopod in shallower waters, the Hadal amphipod stores energy in its body to survive the long intervals between meals. There are also giant sea cucumbers in the Hadal Zone. The Hadal sea cucumber, Elpidia, can reach lengths of over 8 inches. It crawls slowly across the trench floor, feeding on organic particles in the sediment. Its large size may be an adaptation to the cold temperatures and scarce food of the Hadal environment. The Hadal Zone is the least explored part of the deep sea. It is the most difficult to reach. The pressure is extreme, the conditions are hostile, and the cost of exploration is very high. Only a handful of expeditions have ever visited the deepest trenches. We know almost nothing about the life that exists there. But what we do know suggests that the Hadal Zone follows the same rules as the rest of the deep sea. Cold temperature, food scarcity, and reduced predation lead to large body size in some groups of animals. The Hadal Zone may have its own giants, creatures that we have not yet discovered. The exploration of the Hadal Zone is one of the great frontiers of deep-sea science. It represents the last truly unexplored realm on our planet. New technologies are being developed that will allow us to explore these extreme depths more effectively. Autonomous vehicles, advanced pressure-resistant cameras, and improved sampling equipment are opening up the Hadal Zone to scientific study. In the coming years, we may discover new giants in the deepest trenches, creatures that have evolved in isolation for millions of years, untouched by human knowledge. The Hadal Zone is a reminder that the deep sea is not a single environment. It is a series of environments, each with its own conditions, its own life, its own giants. From the mesopelagic twilight zone to the abyssal plains to the Hadal trenches, each depth zone has its own story, its own mysteries, its own giants waiting to be discovered. The deep sea is the largest living space on Earth, and we have only begun to explore it. The giants that we have met in this journey are just a small sample of what is out there. There are more giants in the darkness waiting for us to find them. What new giants will the next generation of explorers discover? Will they find a squid larger than the colossal squid in the unexplored trenches of the Pacific? Will they discover a jellyfish with a bell wider than a house in the midnight zone of the Atlantic? Will they confirm the existence of a giant fish in the Hadal Zone, a true leviathan of the deepest depths? Will they at last see the bigfin squid in its full glory, arms trailing for 30 feet or more through the dark water? These are not idle fantasies or empty dreams. They are open questions, possibilities that remain because we have not yet looked. The deep sea is the largest habitat on Earth, and we have seen less of it than we have seen of the surface of Mars. The giants that we know are the ones that have floated into our nets, washed up on our shores, or drifted across the path of our cameras. The giants we do not know are still out there, in the darkness, waiting to be seen for the first time. So tonight, as you drift towards sleep, let your mind wander down to the deep, to the Hadal trenches, where giant amphipods crawl slowly through the sediment, to the abyssal plains, where giant isopods patiently wait for the next foodfall, to the mesopelagic zone, where oarfish undulate in the dim light, to the southern ocean, where colossal squid fight sperm whales in the cold darkness. These are the worlds within our own world. These are the realms of the giants, and they are waiting, always waiting, in the depths, in the silence, in the cold, endless dark.